Hello, everyone. Welcome to the 2024 DAFoam Workshop. And my name is Ping He. So very glad to see you all here. We have actually about 50 people signed up for the workshop, but I only see 20 people here. I guess they will join later. All right, let's go to the next slides. Today we have three main objectives for this workshop. And first, I will introduce some new features from DAFoam, and then we will have DAFoam users share and present their latest research. And we will also discuss, which I believe it's the main topic of this workshop, is how to promote a more interactive community. Okay, so here is the schedule we have for today. We have a morning and afternoon section. In between, we have about 1 hour break. So in the morning, we have, let me see, 5 presentations. And in the afternoon, we have 3 presentations. And at the end, we have discussion. So I forgot to mention in the morning, at the end of the discussion, we will have, at the end of the presentation, we have about 1 hour discussion about how to promote a more interactive community. Okay. All right, let's get started. I'm going to go first. Let me know if you can see my screen here. Yeah. Okay, so introduction to DAFoam's new features. This is the new features since the last workshop. A quick reminder that in the previous, we had 2 workshops, one in 2021, the other is in 2022. And in the first workshop, we focus on how to use DAFoam mostly. We talk mostly about the details of the configuration files, how do you set out a case. We also demonstrate a very simple aerodynamic optimization case. In the second workshop, which is in 2022, we focus mostly on how to use the new MDO feature and also how to you develop a new features, code feature. So if you're interested in how to use and how to develop DAFoam, please refer to these 2 workshops. And today we will talk something different. First, I will very briefly talk about the new features since the last workshop. Last workshop was like 3.0.0, and this is the first time we developed the interface to OpenMDO and MFIS that enables, for example, Aero-structural Optimization. After that, we developed a steady-state field inversion machine learning capability, which is mostly it's a contribution from Omi Bida from the University of Sheffield. And then we also create some Python callback function such that you can call a Python function from the C++ layer and some other features. And because, for the time being, and today I'm going to focus on 3 main features. They are conjugate heat transfer optimization capability. And the second one is the time resolve unsteady optimization. The last one is that we have a new field inversion machine learning interface. Okay, unsteady aerodynamic shape optimization. So if you use DAFoam before, you probably know that we can do only steady state design optimization. And very recently, we developed we call the time accurate unsteady adjoints and implement that into this DA pinpoint solver that allow us to optimize flows, unsteady flows. And here I show you a very simple example, which is a DAFoam tutorial of aerodynamic shape optimization for unsteady flow over a cylinder. The objective function is the time averaged drag. You can imagine that because it's a cylinder, you will have periodic flow. So we are trying to minimize the time averaged drag. By changing the FFT points, if you look at the right figure, in the X direction, we have a volume constraint. Okay, this is the case setup. And here is the optimization results. And you can see that, first of all, the drag was reduced by 18%. And this, the left-hand side is the baseline design. The optimized design creates like bow tail-like geometries to reduce the drag, which is consistent with our intuition. And to further confirm that, it's this slide shows you the time series of the CD and CL, and comparing the baseline and optimized design. You can see that drag is indeed reduced. Lifts remains the same, but the optimized design seems to have a lower lift oscillation magnitude. Okay, so if you're interested, you can go and check this tutorial. In terms of the unsteady shape optimization in the future, we plan to further extend this with dynamic mesh. So right now we can simulate cases where the mesh doesn't move or change during the simulation. We are now working on, for example, if we want to simulate oscillating airfoil, then we need to do the dynamic mesh. So this is something we are currently working on. And second new feature we want to do is for multi-phase flow. So right now, DAFoam supports only single-phase flow. Of course, eventually we want to further extend it for MDL. We want to couple unsteady aerodynamics and unsteady structures and do this unsteady FSI optimization. Now, these are the three main directions we want to do in the near future. The second unsteady optimization capability I will spend a bit more time on is the so-called unsteady field inversion machine learning. And this is a paper we just published by my students and me in physics fluids. And I will very briefly talk about this new feature in this paper. If you know what this field inversion machine learning is, then you know what I'm talking about. But in case you haven't heard this before, and this is a method that was originally proposed by Kathy Duasami from University of Michigan. And the goal is to augment turbulence model or correct turbulence models prediction error by tweaking the parameters or adding some argument terms. So here you see an example of a ramp flow. So I'm going to first very briefly talk about the setup of the unsteady flow simulation. We prescribe a constant velocity at the left boundary, and the initial flow field is uniform. As you imagine that when we start running the simulation, we can see some unsteady vortex rolling up and propagate downstreams. Okay. Eventually, if you run this unsteady simulation for a long time, and then eventually both of them will converge to a steady state solution. But what we are trying to demonstrate here that if we are interested not only in the final steady state, we're also interested in the transient dynamics of this vortex, then we have to do something different. Here's a case. If you look at the top and bottom figure, the top figure is the simulation results, unsteady flow simulation results from the SST model. The bottom is the SA model. Obviously, in the beginning, their predictions are similar, but eventually you can see the SA predicts very different vortex dynamics and time history than the SST model. So what this FIML can do is to augment the SA model and make it match the SST model. Here's what we want to demonstrate in this paper. But as you imagine that in reality, we don't want to make SA to match the SST. Instead, we may want to make SA to match maybe LES and DNS prediction. Here, just a very simple demonstration that we can do this. And we can then in the future extend it to more realistic data. Okay, then how do we augment the SA model? So the way we do it is that it's pretty standard FIML strategy. We multiplied the SA model's production term by a scalar field beta. Okay, so this beta is a field variable, and then we can further assume that this augment field beta is a function of some so-called local flow features. For example, we identify 4 features. Maybe you want to use other features. And these features are essentially the functions of your flow field that represent some physics. So you can think of by tweaking this beta term, we can modify the behavior of the SA model. So we can modify it in such a way that it matches the SST. This is pretty standard FIML. But for unsteady problems, we have a challenge that, so let's first talk about the steady state problem. So for steady state problem, what you need to do is find optimal beta field, and then somehow build a relationship between the beta field and the input flow features. That's for steady state flow at the final converged steady state. But for unsteady flow, we are interested in the entire time history, which means that both beta and eta, they are time dependent. And if we were to use the steady state FIML strategy, we will have to save all the optimal beta field for each time step for a non-steady case. And you might have 1,000 time steps. That's too expensive. So here's a special challenge for unsteady flow FIML. So in this paper, we propose a solution, which is to couple the field inversion and machine learning by incorporating neural network model into the CFD solver. And the way it works is that usually when we do a steady state field inversion, we first compute the beta field and save them to the disk. And then we do an offline machine learning to connect eta and beta. So in the coupled framework, we have to do this on the fly, meaning that we add a neural network model into the flow CFD solver. Say, for example, we have a governing equation, and then for each unsteady time step, we can compute a flow field. Based on the flow field, we can compute the flow features, and then we call this neural network model to compute an output argument field. And this argument field, if you remember, it will be added to the SA model. Eventually, it will change the governing equation. It will then predict a different flow field. And when we keep looping this until that the flow residuals are very small. So you can imagine that if you're familiar with the neural network, and neural network's prediction essentially is a mapping between the input and output. And this mapping is controlled by its internal parameters, aka the weights and biases of these neurons. And which means that if we change the neurons, the weights and biases, it will predict a different. It will change the behavior of the SA models. Therefore, and we formulate this problem as this. So we still try to minimize and the objective function is minimize the prediction error. Say I want to make the SA model match the SST's prediction by changing the neural network's weights and biases. Okay, this is an optimization problem. And this is for the training data. We use the bottom, the pressure at the bottom wall for the training. So I will go back to it a little bit later. So then we use the framework. We train the SA model, and here is the results. And the top is our reference. The bottom is the trained SSA. If you remember, and 2 slides before I show you the original SS prediction, it did not match the SST, but the train model right now, you can see that match the SST model very well. I mean, the transient vortex dynamics for the entire time history. I want to highlight that. Here is the velocity field. So, but when we do the training, we use only the bottom wall pressure, and which means that using the pressure as the training data can allow us to build an accurate model that matches the SST for the velocity field. This is exciting. And then we further evaluate performance by checking if this train model can be generalized for some unseen conditions. And the reason we want to do it is that eventually we want to use this train model in an optimization such that it can predict flow in a similar setup. Okay, so here we use the model that is trained based on the 45-degree ramp. And then we use the same model to predict a 60-degree ramp. And the right-hand side is the prediction results. Top is the reference, middle is the original prediction. You can see that it doesn't match the SST reference. But the bottom one is the train model. Again, this train model is trained based on 45-degree ramp case and predicts 60-degree ramp case. You can see that the prediction is good enough. We also demonstrate another prediction. In this case, we predict a different ramp angle and different Reynolds number. You can see that agreements is also very good. Okay. In addition to this unsteady field inversion machine learning capability, we also create a new field inversion interface that has these features. First, we support all existing turbulence models, and it supports adding multiple argument fields. Like you can add beta field for one equation, you can add beta field for multiple equations. Right? Say, for example, you have the k omega equation. And And we support couple and decouple field inversion in machine learning. And we support loading a pre-trained neural network models for prediction. You can train your neural network model offline. You can load the model in, and you can do the prediction. And then we also add a new object function called variance. And unfortunately, we don't have a lot of time to talk about the details of each features. But if you're interested, we can talk about that in the discussion section. Again, this is a tutorial. If you're interested, you can get some more information from this link. In the future, again, we want to further extend this for dynamic mesh and multi-phase flow problem. Eventually, we want to enable the capability to use a machine learning trained model in design optimization. For example, we know that the RANS model's prediction for CL max, for example, is not very accurate. Hopefully, we can train an accurate RANS model such that we can do an optimization that maximize the CL max, and while minimizing the cruise drag, something like this. That's our goal. And I guess Omid will talk a little bit more about it later today. Okay, so next I'm going to talk about conjugate heat transfer optimization capability. If you remember in the last workshop, we showed aero-structural coupling. Now in this version, we fully extend the coupling to aero and thermal. And this is just a diagrams that shows you how do we couple aero and thermal together. Again, this is implemented in OpenMDL and InFIS. We have a fluid domains, we have a solid domains. They exchange some thermal data, and then we can do conjugate heat transfer. So I will not spend a lot of time talking about details, but I want to highlight that we use a transfer scheme that is robust and efficient. This is very similar to the one used in OpenFOAM. It can make sure that the temperature and the heat flux are consistent between the fluid and solid in the conjugate heat transfer simulation. So today I'm going to show you two very simple cases. This is something we are still working on, and we submit a few papers to the SciTech. And then after we publish the paper, we should be able to provide some tutorials. But here is the test case. One is to the channel flow case. We have the hot fluid and a cold fluid, and then they flow in the opposite directions. In between, we have this blue one is a solid that can exchange the heat flux between the hot and cold fluid. And the right-hand side is the temperature profiles. You can see that the temperature matched at the interface. If you check the heat flux, they also match. And this table shows you the total derivative verification for the aerodynamic functions, and since the derivative is accurate, but for some reason for the thermal function, for example, heat flux, and this one, the derivative is not super accurate, and we can still do optimization for it, but we are currently working on why, figuring out why this is not very, very accurate. Another case I want to show you is that we managed to run our first conjugate heat transfer optimization for U-bend pipe. And this U-bend pipe is widely used in internal heating or a lot of heat exchangers. And we try to, the objective function is the weighted pressure loss and heat flux by changing the pipe shape. And our boundary conditions that we fix the temperature at outer wall. You can see that although it's hard to see, we have a solid domain here. So here's the baseline design. It is an optimized design. My students are working on this. We just submit abstract to the 2025 SciTech conference. In the future, we want to develop the transient heat transfer capability and to look at the time history of the temperature instead of the final steady state temperature. In terms of other applications, and we are looking for example, the battery heat transfer and some other heat exchanges for the conjugate heat transfer optimization. Yeah, I believe this is all the slides I have. Thank you. Any questions? We have, let me see. We have about 10 minutes for questions. You don't have to ask a question for this particular presentation. If you have any other questions, please let me know and we can talk about that.
Hello,
Yeah.
Professor He.
Hey, you say, yeah. How are
My name
you?
is Yufei. Good. Thank you for your presentation, and I really appreciate that you can make the code open for us, and we have done some work based on the DAFoam. Later, my PhD student Chen Yu, he will provide present a work based on the DAFoam. I have a question that you mentioned that you can support existing turbulence models, all of the turbulence models. Is that true? I'm wondering that if you can support the Reynolds stress models or transition model.
Okay. Thank you for I'm very glad to hear that DAFoam is useful for your research. And regarding your questions, I guess I want to clarify this a little bit. That by saying supporting all existing turbulence model, I mean that before we have to develop a new turbulence model. Say, for example, in an old interface, we have to create a turbulence model that we might call it SA field inversion by changing a lot of things. Now we have a new interface such that I add these argument fields for all the existing turbulence models. Say, for example, I add an argument field called beta nu theta to the SA model. I add an argument field called beta k to the k omega equation. And same thing for the omega equation, such that in the field inversion, you can easily say, I want to argument this field, say beta omega. This is flexible to use. But in terms of the question about the transition model, so I guess Karim and Karim, can you confirm that will you present something that, because your topic is about turbulence transition, will you use a transitional model like K omega SST LN?
Yeah, so I use two approaches. The first one is to use a transition model for field inversion, and the other one is to do field inversion for a turbulence model.
Great, thanks. Yeah. Thanks for confirming this. Yes, we do have for example, the K omega SST LN model differentiated. In theory, you should be able to use that for the field inversion. We also add the argument fields to all the four equations for these turbulence models. But we haven't really, other than Karim, I personally haven't gotten a chance to test if it works or not. But since that Karim got some results, maybe we will show it later today. But yeah, the problem for turbulence transitional model is that some of the functions are not continuous, which might have some problems for gradient-based optimization. Essentially, at some points that the gradient is not well defined, that sometimes we get some wrong derivatives. Other than that, yes, that model is ready to go.
Okay,
can I add something?
Yeah.
Yeah, so transition model I used is something that wasn't existing in OpenFOAM, so I added entirely a new transition model and did field inversion for this.
Oh, you're not using the K omega SST LN.
Yeah.
Gotcha. So if you can make it open source, that would be great.
Okay.
Yeah. Okay, we can talk about that when you present. But thank you. Yeah.
Thank you. I have another question. My students tested the compressible solver of OpenFOAM, and they said the compressible solver is not very robust. Do you have this problem?
Do you mean the transonic flow compressible or just subsonic flows?
Transonic flow.
Okay, yeah. So OpenFOAM has the DAFoam and OpenFOAM has the capability to do transonic flow, but it's not using, for example, roll scheme or some other shock wave capturing schemes, which means that I personally ran a few cases, for example, the RAE 2822 cases, and that the agreement between the DAFoam solver, which in this case is row simple C form, agrees reasonably well with the some other, for example, AD flows results and SU2 as well. But if you are thinking of more complex cases, we haven't really tested a lot because DAFoam, I assume most of the users use it for incompressible flow or subsonic flows. For transonic flows, sometimes I agree that it's not as robust as, for example, AD flows. In this case, maybe AD flow is a better choice for transonic or supersonic flow. That doesn't mean it cannot handle transonic flow. It can handle simple transonic flow. If you're thinking of a very complex case, like it definitely cannot handle supersonic flows. But your Mach number is like, an Airfoil is like 0.7, 0.8-ish. Maybe it can do it okay. So when you say it's not very robust, do you mean that the flow doesn't converge, the adjunct doesn't converge, or the optimization doesn't converge?
That might be both.
Okay, yeah, we add upper and lower bounds mechanism into this zone simple C form. Sometimes we notice that the flow can just diverge, but other than that, maybe you have to look at a specific case. If you can maybe post a question and post, if you can share the case, then maybe we can take a look at why it doesn't converge, and we can share that on the GitHub's discussions. I think I will talk about that at the end of the at the end of this morning section. We can have a discussion in terms of how do we best, interact. Yeah.
Okay. Thank you.
Yeah. Thank you very much for the question. Any other questions? Okay, if no more questions, I guess it's also the time to move on to the next presentation. And I believe our next presenter is Chenyu Wu from Tsinghua University. And I'm going to start sharing, and his topic is more generalizable data-driven turbulence models based on field inversion machine learning using DAFoam. And now I'm going to start sharing, and Chenyu, if you are here, and maybe you can share your screen and
Okay, is my audible?
Yes.
Am I audible? Yeah.
Yes.
Can you see my screen? Yeah.
Yes.
Okay, so I'll go on to my presentation. So hi everyone, I'm Chenyu Wu from Tsinghua University. Today I will introduce you the robust data-driven range turbulence modeling using conditioned field inversion and symbolic regression. I will first talk about the research background, and then we will focus on the model construction, and then we will talk about the results. And at last, we will draw our conclusions. Now let's look at the research background. So why do we do the turbulence modeling, and why do we still need range turbulence models? For the first question, that is because the direct numerical simulation still costs a lot nowadays. The complexity of the DNS is proportional to the third power of the Reynolds number. And in engineering, the Reynolds number can be as large as 1 million or even higher, causing the DNS prohibitively expensive for practical cases in engineering. So people want to use turbulence modeling to lower the computational cost. For example, they use the scale-resolved method like the LES or DES to resolve relatively large-scale turbulence and model the rest of them. And this kind of turbulence modeling methods are relatively accurate, but although it is definitely cheaper than DNS, but they are still quite expensive. And another kind of turbulence modeling method is the RANS method, where the model just models all scales of the turbulence, and this will definitely cause error, but they are relatively cheap. And according to Spalat, RANS will continue to be the workhorse of CFD in the coming decades. That is because the scale-resolved methods like the LES or DES are still too expensive for tasks such as the optimization. And in engineering, only the time-averaged quantities such as the force coefficients are of the primary interest. And RANS can get these averaged quantities directly, and is very cheap. So it still has practical value to investigate the RANS turbulence models. However, the RANS research has encountered a stagnation after 2000. Few influential turbulence models have been proposed since then. Popular SST and SA model still have many problems in like separated flows or secondary flows. For example, let's look at the right corner. You can see the SA and the SST model cannot predict the lift coefficient of the iced airfoil accurately because they cannot resolve the separated flow caused by the ice. And in a 3D shockwave case where an induced separation exists, the location of the shockwave is has a lot of error if you are using a traditional turbulence model. However, these complex flows are still very important in engineering, and we want to resolve them accurately. So we still want to enhance the RANS model's accuracy in these separated flows. In recent years, the data-driven methods have emerged, and they might be a new way to break this stagnation because they might discover hidden relations that are hard to find by human researchers. And these hidden relations might help us to improve the performance in the separated flows. Among these data-driven methods, the field inversion and machine learning method is very popular because it can deal with very sparse training data, making it widely applicable. And in the field inversion step of the FIML, a correction term beta is incorporated with the transport equations of the turbulence model. Let's take the SST model we will be focusing on as an example. The correction term beta will be multiplied to the destruction term of the omega's equation. And then the spatially varying correction term will be determined by solving an optimization problem that minimizes the discrepancy between the RANS prediction and the high fidelity data as shown in the central figure here. And then in the machine learning step, machine learning model will be constructed to predict the corrective term beta obtained by the field inversion step. And at last, this machine learning model will be integrated back into the transport equations and be applied to new cases. The field inversion and machine learning method has achieved great success in separated flow correction, like the 2D airfoil store case and the 3D hail cases. It can fix a wide range of flows using a various kind of data, even the data produced by older experiment where the sensors are very sparse. However, the models constructed by FIML along with other data-driven methods generally have some problems. First, they might be very hard to interpret because many of them are just black box models like neural networks or the random forests. And secondly, they are very slow to compute because there are many parameters in the neural networks or the random forests, and it requires a lot of floating point operations to forward pass them. And at last, they are very hard to generalize. Sometimes they lack robustness. Here, the robustness refers to the model's ability to preserve the baseline model's accuracy in simple wall-attached flows, such as the zero-pressure gradient flat plate or the turbulent channel flow. For the first two problems, a research of my own has shown that it can generally be solved by using symbolic model in the machine learning step to construct a compact expression for beta. And for the last problem, it is still very hard to solve. No matter you are using the black box model or you are using the symbolic model, if your model is only trained on separated flow cases, it will be very hard for them to accurately compute the zero pressure gradient flat plate. And if the pressure gradient exists, like in the NACA 0012 airfoil case, this scenario may be even more severe. Like you can see on the right side, the FIML model in this case overestimates the friction coefficients by a lot. However, Spalat argues that the generalizability to simple wall-attached flows, that is the robustness, is highly important because it is essential to estimate the friction drag. And sometimes the friction drag can constitute a large portion of the total drag. And adjusting the law of Wahl to enhance the separated flows accuracy is physically wrong because we know the law of Wahl is right. And by adjusting the law of Wahl, we are basically doing some overfitting, and this will definitely destroy the generalizability of our models. So considering the importance of this problem in this study, we try to develop an improved field inversion method and construct a robust data-driven model that preserves the accuracy in simple wall-attached flows. Now let's look at the model construction. Now let's talk. I'll talk about the basic idea behind our model construction. So we think that the error comes from the distorted basic calibration in the boundary layer. So if we look at the two blocks on the right side, you can see that in the first block is the omega equation of the SST model and the related calibration of the log law. And in the second block, you can see the field inversion equation and the related calibration on the log law. So by comparing the second line of each block, you can see that the calibration for the log law stands in the field inversion equations only if beta equals to 1 uniformly in the boundary layer. But sometimes field inversion tends to adjust beta in the boundary layer, because adjusting the boundary layer can indeed influence the separation downstream, though it may not be physically sound. So we try to resolve this problem by multiply the correction term beta with a filter function FD, like we are showing here. A typical distribution of the filter function FD is shown in the right corner. You can see the FD is uniformly 0 in the boundary layer and is 1 elsewhere. So it makes any adjustment in of the correction term beta in the boundary layer non-consequential. It prevents the correction in the boundary layer on the model structure level, which means that the data produced by the field inversion will have beta uniformly 1 in the boundary layer. Since the gradient of the objective equals to 0 in the boundary layer thanks to the filter function FD. And the model trained on the data will have the model trained on the data will have no influence in the boundary layer since it is filtered out by FD. So using the filter in the field inversion process is referred to as conditioned field inversion from now on, that is the FICND. The only difference between the proposed FICND method and the classic field inversion method is the formation of the omega equation. For the FICOS method, the parameters of the model are freely modifiable both inside and outside of the boundary layer because the correction term beta is directly multiplied to the destruction term of the omega equation. But for the FICND method, as you see, the correction term is first filtered out by the FD and then multiplied to the destruction term. So the parameters are only modifiable outside of the boundary layer and they remain fixed in the boundary layer. So this can protect the basic calibrations in the boundary layer. Here, the FD function we are using is originally proposed by Spalat for DES. And in the rest of the study, we will show that the model constructed by the proposed FICND method has similar performance compared with the model constructed by the FICOS in separated flows. So now no downgrade in the separated flow correction for using our conditioned field inversion method. And only the model constructed by FICND has acceptable performance in simple wall attached flows such as the zero pressure gradient flat plate. So the performance will increase by using our FICND method to construct the models in simple wall attached flows. Now let's look at the model construction. First, we'll have to conduct the FICOS and FICND on the curved backward facing step case where the Reynolds number is around 14,000, and in the NASA hum case where the Reynolds number is around 1 million. DAFoam is used for the implementation of the conditioned field inversion and classic field inversion, and all the computation, all the optimizations are done by DAFoam. You can see in the central row that both methods can decrease the velocity error significantly. And if you look at the left corner, you can see that the FICOS tends to correct the boundary layer, while the FICND correction concentrates in the separated shear flows. We then mix the field inversion data on the curved backward facing step case and the NASA hum case to capture both the high Reynolds number characteristics and the low Reynolds number ones. Then closed form models are pursued by using the symbolic regression by using the code PYSR. And the features we are using are listed in this table. As you can see, we are using the invariance of the strain tensor, the rotation tensor, and the vorticity Reynolds number, and the ratio of the turbulence production and dissipation, and an additional feature called eta that is discovered by our previous symbolic regression studies. And the trained models are shown in this table. You can see in the first row is the symbolic model trained on the classic field inversion dataset, and in the second line is the symbolic model trained on the conditioned field inversion dataset that is called the SR-CND model. And then we apply the SR-CLS and the SR-CND model back to the training set. You can see these two models can both reconstruct the the beta field produced by the field inversion. So our training is quite effective. Now let's look at the results. All the results are obtained here are by using the OpenFOAM unless otherwise specified. Now let's first look at the training set. The first training case is the curved backward facing step case. As you can see on the right column that the SR-CLS and the SR-CND model indeed improve the baseline SST model's accuracy in terms of the location of the reattachment point, and the velocity profiles in this here suggest the same. And the predicted beta field equals to 1 in the boundary layer for the SR-CND method, while the SR-CLS gives a beta larger than 1 in the boundary layer. However, the friction coefficient is not significantly influenced because the deviation of beta from 1 in this case is quite small, and the Reynolds number is relatively low. And another training case is the NASA hum case. Here on the right column, you can also see that the reattachment points accuracy is significantly enhanced by using the SR-CLS and the SR-CND model. And the velocity profiles also suggest the same. However, the SR-CLS model gives a beta larger than 1 on top of the hump, which results in a 60% increase in the mean square error of the friction coefficients, as you can see in this central bar plot here. But the SR-CND and the SST model have similar accuracy in the wall attached flows. So the SR-CND model indeed protects the attached boundary layer here, while having the same accuracy in the separated flows as the SR-CLS model trained by the classic field inversion method. Now let's look at the test cases. The first one is the periodic hill. The SR-CLS and the SR-CND model can both predict the separation well in the periodic hills, as you can see on the right column. And the grid convergence property of our proposed models are quite nice. As you can see, the integration of the friction coefficients saturates quickly as we increase the density of the mesh. However, the beta distributes diffusively for the SR-CLS model with beta larger than 1 in the upper boundary layer where no separation exists, while the SR-CND gives a very concentrated beta distribution that focuses on the separated shear layer. So the SR-CND model again protects the boundary layer here while having the same accuracy in the separated flows. Now let's look at another 2D test case that is the 2-element airfoil NLR 7301. In this case, as you can see in this table, both the SR-CLS and the SR-CND model can increase the accuracy of the maximum lift coefficients and the stall angle of attack, while the SR-CND model can have an error in maximum lift coefficients that is smaller than 1%. That is a very good performance. And the beta field is mainly increased to a large value in the mixing region of the main flow and the low speed region, as you can see here in the upper left corner. This will definitely increase the momentum diffusion from the mainstream to the low speed region, and thus delaying the separation on the flap, as you can see in the last row. And all the computation here are performed by CFL 3D. So that is because the closed form model makes the implementation of the model in the CFL 3D very easy. And at last, let's look at the 3D test cases, the simplified car bodies. Both the SRCOS and SRCND model can generalize to these 3D complex separated flows nicely. That is the SAE car body and the Ahmed body. As you can see, the error in the velocity profiles and in the drag coefficients are significantly decreased by using our models compared with the SST model. And the grid convergence property is also nice. When we increase the mesh's density, the drag coefficients converges to a constant value. So both the SRCOS and the SRCND have good ability in fixing these 3D complex separated flows. Now let's look at the wall attached flows. In the zero pressure gradient turbulent boundary layer and the NACA 0012 airfoil at zero angle of attack, only the SRCND model gets the correct result. The SRCOS model gives a beta larger than 1 around y plus around 100, which results in a serious overestimation of friction coefficients and the wrong log layer slope, as you can see in the first 2 panels here. And when the pressure gradient is presented, the SRCND model and the SST model still give very similar results, as you can see in this NACA 0012 airfoil case, while the SRCOS model again overestimates the friction coefficients, which will definitely increase the drag coefficients. Now let's come to our summary. Both the SRCND and the SRCOS model have strong generalizability in separated flows. So no worry that using FICND will downgrade the data-driven model's ability to fix separated flows. And the SRCND model constructed by the FICND method can preserve the accuracy in the wall attached flows, while the SRCOS model constructed by classic field inversion method cannot. The model is now incorporated into OpenFOAM's turbulence model community, which is announced in the release note of OpenFOAM version 2406. So everyone can download our model and use it now. And the model is used in a detailed configuration of electric vehicle, which enhances the accuracy of drag coefficients prediction significantly. Now, at last, I'd like to express our special thanks to Ping He and all the contributors of DAFoam. Without them, the work in this report can never be done. And here, the figure shows my early discussions with Heping on the GitHub discussion page. Heping has always been very patient and nice to answer my some silly questions while using the software or developing it for the first time. So I'd like to thank Heping again here. I'm a big fan of Heping. Yeah. Okay. Thank you, everyone. We're open to questions now.
Thank you very much, Tony. Very glad to hear that. I'm very also excited to see that you shared your train models to the new release of OpenFOAM. That's awesome news. Thanks.
Oh,
okay.
Yeah,
we can take questions from general audience. Any questions for Chenyu? Maybe I can start with my question. So I just want to confirm one thing is that the models SST you trained it based on a specific 2D cases or many other cases?
Your
training data.
I'll share my screen again. Can you see my screen now?
Yes.
Okay. The training set includes 2 cases. The first one is the curved backward facing step case, and the second one is the NASA hump case. So I just performed the classic field inversion and conditioned field inversion on both cases, and then I mix the data sets, mix the two different geometries data sets, and then I train the model. So the training set has basically 2 cases included to capture both the Reynolds number, low Reynolds number characteristics and the high Reynolds number characteristics. Yeah.
Okay, so because this is very exciting because it seems that you train it with only 2 data set, and then you can predict flow from completely different geometry, completely different Reynolds number, and other parameters. That's great. Okay, that's exciting. And another question I have is that in terms of the boundary layer, you set beta equals 1 in a boundary layer, and outside the boundary layer, you will use the correction. So when you do the prediction, I guess you need to do the same thing. So
yes, I still have to filter the beta field like here. You can see, have to filter the beta field by the filter function FD. In the prediction stage.
Gotcha. So is it very expensive? How expensive it is to add to this field? For example, for a 3D case, it will just not. I guess my question is that compare in terms of computational costs between using the SA model and your train model.
I think I've compared it with the SST model. In the last case, in the last case here, the electric vehicle case, and I don't think just using my model will increase any computational overhead. So the difference between them is not that significant, I think.
Okay, that's good. And because I guess because from our experience, if we use a neural network model, then the cost will definitely increase. Is this because we use the symbolic regression that the relationship compact?
I think so. I think so. The symbolic regression can just really decrease the computational cost because the expression is very simple. You just need to do some algebras and then you can get the results.
Okay, that's good. That's good. Very good. Very nice work. Thank you for sharing.
Thank you.
Okay. Other questions?
Yes, I have a question.
Sorry, go ahead.
Okay, so when you train the beta field, do you train the entire field or only extract beta in the where it actually changes?
Oh, in fact, I extract the entire field and then I do something like downsampling. I preserve all the cells that has a beta larger than, for example, larger than 1.05. And then for the beta that is smaller than 1.05, I will downsample them and makes the samples that has smaller beta and larger beta has approximately equal numbers in the training set.
Okay.
Okay, thank you.
Hi. Nice presentation. I missed the starting parts of it, but I'm just curious to know a little bit more about this symbolic regression that you performed. So, can you tell us a little more? I'm not sure if I missed it, but what's the cost of performing this symbolic regression? Can you tell us a little bit more about it?
The symbolic regression. We are performing a symbolic regression by using the software called PYSR. It is also an open source software. You can search it on GitHub. And the training process of using the symbolic regression is it has no different from using the scikit-learn or some other things. It is very simple to use. But by now, a main drawback of using the symbolic regression is that the PYSR code or other evolutionary algorithm codes they cannot handle a large data set.
I see. Okay, right. No, because there are a lot of symbolic regression. In fact, I was going to speak about one today. There are a lot of symbolic regression tools available, right? So I just wanted to know if there was, apart from the fact that it's open source, was there any particular reason for choosing PySR? I was just curious about it. That's all.
It's just because it's open source.
Right. Fair enough.
Okay. Okay.
Fair enough.
Thank you.
Yes, thank you.
Thank you.
And following on this question. It seems that the symbolic regressions, I guess, because on the left-hand side in the table, you mentioned you provide 1, 2, 3, 4, 5, 6 features, but symbolic regression might drop some of the feature. It's not important.
Yeah.
Okay.
Yeah, it generally just drops many features if you limit the complexity of the expressions. So, yeah.
So I haven't gotten a chance to use it before, but do you need to prescribe the functional form? For example, in the first
yes. Yes, you have to. Here I didn't show that. I've prescribed the tangent edge and the the plus, the minus, the multiplication, the division, and I've also added the min and max and exponentials. That's all the steps I'm using. Yeah.
You do need to prescribe some functional forms, and the symbolic regression will find those coefficient, unknown coefficient for you. Is that how it works?
No. You provide the element functions, and then the symbolic regression will combine them, like combining a tree or something like that. Combine these element functions and get the final expression. So the final expression can be expressed as a tree whose leaves are the variables or the element functions you specified. Yeah.
Gotcha. But the reason I asked was that I wonder if this process is differentiable, meaning that can we somehow, incorporate it in a coupled optimization sense. Anyway, so I can take a look at if this is differentiable or not. Yeah. Thanks. Okay. Any other questions? Yeah, we got a question from the chat. What are the key limitations of your approach? Also, how generalizable do you think the SR, CMD, and CRS is with regards to separate flows? Can you attack any separate flows? Yeah, we get a question in the chat.
So,
Can you answer the question? Yeah, it seems that you're muted again. Okay. How about this? Because of the time being, and Chen, we have to move on to the next presentation. How about you answer the question in the chat? Yeah, sounds good. Thank you. All right, let's go to the next speaker. Our next speaker is Bernardo Bassini from University of Michigan. His topic is multidisciplinary design optimization of propeller-driven aircraft. So Bernardo told me that he couldn't join today. That's why what I'm going to do is that he pre-records a video. So I'm going to do is that I will just play his video. Okay, so let me share the screen. And so let me know if you cannot hear his presentation. Okay, I'm going to play his.
Hello, my name is Bernardo Bassini, and today I'm excited to share my recent PhD work titled Aerodynamic and Aero-structural Design Optimization for Propeller-Driven Aircraft. My work is motivated by advanced air mobility, or AAM, and as shown in this visualization, this is a new idea for transportation into, out of, and within urban and rural environments. And so the idea is that we can develop a range of different vehicle types, as shown here, that can accomplish different missions to relieve the stress in our transportation systems. And the real thesis for advanced air mobility is for anyone to fly from here to there, anytime, anywhere. The landscape of vehicles being developed is quite broad. Here is a schematic with just a few of the current designs, and you can see that they range from single passenger, very small aircraft to very large aircraft that you may not be surprised to see at an airport today. And these are all targeted at different missions, but what is common to just about all of these designs is the fact that they have wings and they have propellers. And so we're looking at how we can optimize a range of these vehicle configurations using DAFoam and similar tools. In recent years, there have been studies into technical development necessary for advanced air mobility, and these are 10 areas that were identified by NASA back in 2019, and they range from ease of certification and affordability to ride quality, life cycle emissions, and safety. But there are two that were seen as truly significant barriers to technical development: community noise and vehicle efficiency. And this is what I focus my PhD work on, and I'll present on just some of the results today. Community noise is important because if these vehicles aren't quiet, then they won't see wide-scale adoption because they'll actually add disruption instead of improve congestion. They also need to be very efficient because if they're not efficient, we're being detrimental to our environment. And so once again, they won't see wide-scale adoption. So we really need to make progress on community noise and vehicle efficiency. So the motivation for me in this work is that AAM vehicles must be both efficient and quiet. My objective is to improve AAM vehicle efficiency using multidisciplinary design optimization. So let's jump into what is multidisciplinary design optimization for aircraft applications. Let's say we're designing the outer mold and the structure of an aircraft, and we can change things like the wingspan, the airfoil shapes along a wing, and structural sizing variables. And we're interested in quantities such as fuel burn and structural stresses. On each design iteration, we'll update the wingspan, airfoil shapes, and structural sizing, and look at the consequent fuel burn and structural stresses of that specific design. And we'll slowly iterate to improve the fuel burn while making sure that we don't make a design that will fail because the stresses go too high. If you want to formulate this problem mathematically, we can say that we're minimizing some function f of x, which is the objective, with respect to design variables x and some constraints c of x. Now, we are not the first to do this for AAM applications. There's been some work in large-scale vehicle optimization, largely with low-fidelity methods, some trajectory optimization of a tilt-wing vehicle, mission optimization of a conventional takeoff and landing electric aircraft, and economic and market outlook optimization that designs both the aircraft and the mission in one go. To do all this work, we use gradients, and gradients are instrumental for efficient optimization. And this is because gradient-free methods, where you don't use model derivatives, scale very poorly, especially as problems get larger. So you can see on the top side of this graph that shows number of function evaluations with respect to number of design variables, the gradient-free line is quite steep. And so when we start hitting maybe 10 or 100 design variables, we get a prohibitive number of function evaluations necessary, looking at even 10 to the 7th. When we use gradient-based methods, we actually can keep that line substantially more flat, especially using analytic methods. So we can look at these very large aerodynamic and structural design problems and still have them be feasible as optimizations. To just show an example of the power of aerodynamic shape optimization, I'll show this video that goes from having this uninformed circle into a transonic optimized airfoil in under 100 iterations. Now the question for us is, how do we apply this sort of optimization to advanced air mobility? To do this, we start with OpenMDAO. OpenMDAO is a modular framework for gradient-based optimization with coupled models. You can add, subtract, and change components that interface with each other, and you can plug them all into this framework. On top of OpenMDAO, we've developed a toolkit called MPhys, and MPhys is a standardized multi-physics library for design optimizations. So you build up optimization problems that are based on this multi-point group that have different flight scenarios. Say you want to look at a vehicle's hover, climb, cruise, and maybe even landing flight scenarios, so you can build all of these up inside of MPhys. And you can look at things like propulsion, structures, and aerodynamics and plug them all into an optimization problem. Understanding what the computational code stack can be important. So the foundational layer for the optimizations is all OpenMDAO. OpenMDAO handles how information is passed between components and provides an API that we can plug into. On top of this, we have MPhys. So let's say we're looking at community noise again and vehicle efficiency. We can have one flight scenario where we're particularly interested in acoustics. We can have another flight scenario where we're particularly interested in structures. So we have an aeroacoustic and an aero-structural design scenario. On top of that, we plug in whatever physical components we want. So for each of these scenarios, we have a geometry parameterization. That is what gives us the shape of, say, our propeller or our wing or our entire aircraft. We have our aerodynamic solver. That is what simulates the aircraft or the wing. And then we have, in one case, an acoustic solver, in another case, a structural solver. Now, all of the communication starts on the OpenMDAO foundational layer and communicates with the MFIS scenarios. Each of the physical models that are plugged into MFIS communicate through the MFIS layer and with OpenMDAO. They do not communicate directly with each other. So say you wanted to use DAFoam for one optimization, but a different CFD solver for another, you could plug and play whatever components you like into and out of MFIS. And on the outside of all of this is an optimizer that controls the design variables and receives the function values and the gradients so that it can come up with a new set of design variables for the next iteration. For our problem, we're trying to leverage multidisciplinary design optimization, come up with a framework that is discrete adjoint based and uses DAFoam and some other tools to do design optimization for advanced air mobility vehicles. So we start with an optimizer, and the first step is always to define a geometry. This will parameterize our wing, our propeller, and perhaps some other parts of our aircraft. We can run aerodynamic analysis on this design to figure out how the design performs aerodynamically. We can also add structures where we can simulate the aerodynamics and the structures together to understand how the wing bends and how that performs aerodynamically once the wing is bent. And if we're interested, we could, for example, look at aeroacoustics and predict how much noise a propeller is generated when mounted on a wing. The outline of this presentation is in part 1, we'll look at aerodynamics alone of a propeller wing model, and in part 2, we'll move to aerodynamics and structures, which is a blend of the two. First, aerodynamic optimization of a coupled propeller wing system. This is work that was in my PhD dissertation, and we are working on publishing. Aerodynamic optimization of a coupled propeller wing system consists of overall and aerodynamic coupling between two main models. In DAFoam, we do this with two separate models, a propeller analysis and a wing analysis. We run a low fidelity propeller analysis to understand the blade load distribution from the propeller and impart it on the wing. So we compute propeller blade loads, and we put them on an actuator zone that is steady state inside of a DAFoam simulation. We parameterize this with design variables, and we get function outputs. And because DAFoam and the other tools are gradient based, we can get the derivative of the functions with respect to the design variables to perform gradient based design optimization. Now, the methods we use are for the propeller aerodynamic modeling, we use blade momentum theory in a tool that we developed in-house called Helix. And for the wing aerodynamic model, we use RANS, CFD within DAFoam. To highlight how this aerodynamic modeling is done, for the propeller, we use a mix of momentum theory and blade element theory, known as blade element momentum theory, where momentum theory considers propeller as just a stream tube with the propeller being a disk. And instead, blade element theory uses information from that disk and stream tube to compute sectional loads for thrust and drag. For the CFD simulation of the wing, we used Reynolds, Evers, and Navier-Stokes with DAFoam. The propeller blade loads are mapped from BEMT to the actuator zone in the RANS CFD simulation. For our analysis, we ought to first make sure that the computational results we get from DAFoam are reasonable and accurate. So we start with the TU Delft propeller wing interference model, or the PROIM, which is an extensively studied design that has a large suite of computational and experimental data. To begin, we look at verification of the propeller blade load. So this is purely blade momentum theory modeling how the propeller behaves. At an advanced ratio of J equals 0.8 and a free stream flow velocity of 40 meters per second, we have some computational data to compare to. So the dotted blue and black lines and the gray spread are all CFD data, and the orange line is our low fidelity BMT approximation. And what we see here is that the BMT approximation actually does a really nice job of capturing the CFD data practically in real time, instead of needing several hundred processors and fully unsteady results. So we're really happy that we can capture this quite quickly. When we combine both the propeller analysis and the wing analysis to do a coupled propeller wing validation, we compare against experimental measurements shown here as black dots. And we have on the wing, the upgoing blade region and the downgoing blade region, which are regions behind the propeller on the wing. And this top graph is the coefficient of lift along the wingspan. And we see that, especially for the 0-degree angle of attack case, we really get the black dots well with our computational measurements. And we capture also the bubble the bubble going up behind the upgoing blade and the bubble going down behind the downgoing blade of the propeller. For the 4.2 degree angle of attack, we see generally good agreement still, and we capture some increases and decreases due to the propeller blades, even though we get slightly worse agreement. Looking at coefficients of pressure at 35 and 62% span, which again correspond to the upgoing and downgoing blade regions, respectively, we see that again our computational measurements, the lines, align very nicely with the black dots, which are the experimental measurements. So with fully steady state analysis and these two coupled aerodynamic models, we're able to capture these physical quantities that were measured in experiment quite well. So this gives us confidence we can use this for optimization. The optimization problem that we're going to look at is two-part. Part of this study, we want to understand if coupled propeller wing optimization is worth it, or if you should simply just design a propeller and design a wing and stick them together. So the first optimization problem that we'll look at is independent. So independent is we'll optimize the wing drag alone with respect to wing twist and shape design variables with some additional geometric and problem-specific constraints, such as the lift of the wing must equal 550 newtons, and then we have some volume, thickness, leading edge radius, and curvature constraints that are surrogates for other parts of the simulation, such as structures that we don't include. We'll also do a propeller power optimization where we'll optimize simply the orange quantities here, where we'll minimize propeller power with respect to propeller design variables of twist, chord, rotation rate. And we'll have some design variables such as the propeller chord concavity and the chord bounds, which are necessary to make sure the design is reasonable and doesn't break the physical model. And we'll then take these two optimized designs and we'll put them together and trim them to the desired lift condition. On the other hand, we'll leverage the ability of DAFoam
For some reason, I got disconnected. I guess you cannot see my share screen anymore. Can you, any of you confirm this?
Yes, sir, it's like that.
Okay, let me share this again. For some reason, my Zoom just got disconnected. Yeah, so I'm gonna play the video.
and independent optimization.
My bad, I forgot to click the shared the sound.
The location of where the propeller is to allow it to be optimized to be most effective for the wing. Let's begin with the independently optimized designs. So here I'll show a video of the design optimization of the propeller first. In this case, the thrust is fixed to the required 55 newtons, which is the baseline for the optimization, and we get a 5.63% improvement in power to about 6.5 kilowatts. Optimizing the wing, we see how the wing is reshaped over the course of the optimization, satisfying that 550 newtons of lift and decreasing drag about 9.4% over the course of 105 iterations. Post-optimization, we couple these two optimized designs together and we trim them to the desired flight condition to make sure the thrust equals the drag. Now, in the coupled optimized design, we optimize both the propeller and the wing in unison. So I'll show that video here. You see how the propeller jumps around a fair bit towards beginning optimization and then is optimized to a specific point towards the wing tip. We hit the lift constraint of 550 newtons, and we have a trim constraint that ensures that the thrust of the propeller equals the drag plus an offset of the wing. And we see here that we've actually gone down almost 16% in required power. Now, when we do a comparison of the independently optimized and coupled designs, once they're both trimmed, we see that for the independent design, we have a power of a little over 5.7 kilowatts and a drag of 32 newtons. And for the coupled case, we have about 5.6 kilowatts and 30 newtons. So we see a modest 1.7% improvement in power, but a larger 5.6% reduction in drag. Now, where does this difference come from? the results show that the wing design is not heavily impacted by the propeller design. So here we see in blue is the independently optimized design for the wing, and in orange is coupled. And overall, the top part of the graph, the coefficient of lift along the wingspan, is similar between the two cases, and the twist and the thickness are also quite similar, with only minor oscillations in the coupled case. Instead, the propeller design is strongly impacted by coupled optimization. So we see that the axial force, the top graph, is generally quite similar, but the tangential force is much larger for the coupled optimization, as well as the twist and chord, and the rotation rate is much lower. So what this means is that this case has a much higher torque, which induces a substantially larger swirl in the flow, which decreases the induced drag of the wing. So what we find is that in the independent versus coupled optimization, we actually want to compromise the propeller efficiency to improve the efficiency of the overall system. So we see that for the wing drag, from the baseline, we drop about 12% to the independent case. We drop another 5% in drag to get to the coupled optimized design. The propeller power numbers are less impressive in terms of a difference between independent and coupled, where we drop about 14% from baseline to independent, and then we drop another 1.5% to the coupled optimization. I want to highlight the optimization history here and note that while of course we do see an improvement by doing coupled optimization, there is a cost to it. So the coupled optimization is computationally more expensive and takes roughly twice the number of iterations. When we look at the actual time values, we see that the propeller optimization is quite quick. The wing optimization alone is about 10 hours. The trim is about 2 hours, which gives us a total of about 10 hours. For the fully coupled optimization, we run simply one optimization that is 18 hours long, and that's 64, almost 65% increase in time, but it does yield a better result. So the conclusion here is that coupled optimization improves the system performance by compromising propeller efficiency to reduce wing drag. Part 2, Aero-structural Optimization concerning propeller wing interaction, and this is more work from my PhD dissertation that we are working on publishing. Aerostructural analysis and optimization requires two coupled models. We have an aerodynamic analysis and a structural analysis. The aerodynamic analysis passes loads from the aerodynamic analysis to the structural analysis. The loads are then used to analyze the structure, and the structure is deformed, and these deformations and displacements are passed back to the aerodynamic analysis, so we can simulate the performance of a deflected wing. We have design variables that can parameterize these two components, and we have function value outputs. We have all of the derivatives of the internal model, so we have the total derivatives of these functions with respect to design variables, so again, we can do design optimization. And the methods that we use is RAND-CFD with DAFoam for the aerodynamic model. We have a load and displacement transfer tool that handles these loads and displacements between the aerodynamic and structural models, and then we use a finite element analysis tool for the structure called TAX. Now, propeller aerostructural coupling is a little bit different than conventional aerostructural coupling for a wing, and this is because propellers have a thrust, a torque, and an installation weight that all affects the wing structure. So how do we model this? We look at a clean wing, as this is easier for optimization once we remove the complicated intersections and geometries components for nacelles, and we look at a wing box so that it has some spars and some ribs. We connect rigid body elements that allow us to connect to where the propeller locations are and impart some forces and track displacements. With this, we have a simplified version of our wing that we can use for both aerodynamic and structural analysis. To just show an example of how and why we do this, this is a video that shows how the wing is deflected and how the propellers track that deflection over the course of an aerostructural analysis, not an optimization. The changes are subtle, but you'll see that the propeller locations have tracked how the wing has displaced. So not only do we accurately track how the forces are impacting the wing, but we also track how that propeller moves, and we can more accurately model the aerodynamic performance with the actuator zones. We'll apply this methodology to the NASA Tiltwing concept vehicle to design and optimize this vehicle configuration using DAFoam. This vehicle is an 8-propeller vehicle with propulsors distributed along the wing and horizontal tail. In hover, the wing and the tail propellers are oriented vertically so that it can take off vertically and land vertically, And in cruise, everything is oriented like conventional aircraft forward, so it can fly like a normal aircraft. For our case, we remove the nacelles and we model the propellers as actuator zones to simplify the geometry and the optimization problem. We'll have three different scenarios. We'll have a hover scenario that is purely structural to make sure that the aircraft is structurally sound. And then we have a cruise scenario and a maneuver scenario, which ensures that our vehicle can sustain a specific 2.5G maneuver when in flight. For the structure, we use this methodology where we remove the nacelles and we connect to our propeller locations using rigid body elements in our structural solver. The optimization problem we'll look at is multi-point through our different scenarios, but overall we're trying to minimize propeller cruise thrust with respect to a maneuver angle of attack, the wing chord, twist, sweep, and shape distributions, the tail deflection of the elevator, the structural thicknesses of the panels in the tail and the wing. The propeller locations are tracked to make sure they stay a constant distance from the wing, and a cruise maneuver and thrust. So we have 364 design variables. Then we have constraints on the X, Z, and moment to trim this vehicle in both cruise and maneuver. And then we have some additional constraints, for example, a volume constraint to model the space needed for battery packs in the wings, thickness constraints for similar types of constraints, a leading edge radius constraint that's necessary to model or to allow the vehicle to carry out other mission segments such as climb. And then we have a hover and maneuver material failure constraint with a safety factor of 1.5 to make sure the structure is structurally sound. The geometry parameterization is shown in the following animation. So you can see that the tail can be deflected, the sweep can be changed, the chord can be changed. We can change the twist at each wing section. And we can also pull up and down on the freeform deformation grid points to change the shape of the wing. Here's an animation of the optimization history for the cruise and maneuver flight conditions. You can see through this optimization that the maneuver has a much higher structural loading and is closer to failure. But we see, most importantly, that the sweep on the wing is removed, and we see an increased chord at the root and a decreased chord at the tip. This is a frontal view of the deflection of the wing for cruise and maneuver off of the jig shape, which is the baseline. So you can see directly here how our two-way coupling is allowing us to model the wing once it's actually deflected, not just the baseline jig design. The wing distributions for both cruise and maneuver flight conditions maintain aerodynamically optimal lift distribution. So in this top part of the graph, the normalized lift tracks the elliptical distribution quite well, with some oscillations where the propellers are, where we have upgoing and downgoing swirl from the propeller regions. The twist distribution along the wingspan is generally constant, with minor oscillations near the root that is trying to handle some separation between the fuselage and the wing, and an oscillation at the tip that helps decrease induced drag. The thickness distribution with respect to chord increases slightly at the root and then decreases roughly constantly over the course of the wingspan. The planform change here is significant, so the baseline has some sweep with a roughly constant chord wing, while the optimized design has a much larger root chord, much smaller wing chord, and has zero sweep along the leading edge of the wing. So the optimization removes wing sweep, increases wing root chord, and decreases wing tip chord. Something to highlight is that the structural sizing of the wing reaches roughly the minimum bound for nearly all of the structural panels, apart from a few near the root, which of course makes sense because these are the ones that have the largest force. On the other hand, the tail remains quite large even though it doesn't reach failure. What is interesting about this is we have a panel that actually reaches 70 millimeters, which is extremely thick for a carbon composite laminate that we're using. And the reason for this is because the vehicle is not very well balanced in its baseline design. So the structure was optimized to increase weight towards the tail to decrease trim drag in the optimization. Most of the wing panels reach the minimal allowable thickness, and the tail mass is used to improve the overall vehicle trim. To highlight the optimization history, we can see that the convergence tolerances for both optimality and feasibility decreased significantly down to 1e-6, where the optimization exited successfully. Our objective value, which is the cruise thrust, oscillates at the beginning and then stabilizes through the optimization, and the overall aggregated trim residual decreases below the required tolerance. And for the failure of the wing and the tail, we don't exceed our value of 0.67, which is a failure of 1 with a safety factor of 1.5. So gradient-based aerostructural optimization helps us design a feasible and optimal aircraft. The conclusion here is that aerostructural optimization, considering propeller wing interaction, allows us to more accurately optimize a full vehicle configuration. I want to highlight the work that we have done with DAFoam. First, we've done aerodynamic optimization of a coupled propeller wing system. Second, we performed aerostructural optimization considering propeller wing interaction. With this, I'd like to thank you very much for your time and highlight some of our collaborators, including Airbus, DAR Corporation, Hyundai Motor Company, Orb Aerospace, the Politecnico Milano, NASA, of course, Iowa State University, and the Technical University of Delft. Thank you, and I look forward to hearing about your questions after the workshop.
All right, that's the presentation from Bernardo. And any questions? Because I'm familiar with his work, I think I can answer any questions if you have for Bernardo. If no questions, maybe we can chat and ask him about that, his work, and that's his PhD work, and maybe after this workshop. But thanks. Okay, I guess what we can do is that we can move on to the next presenter, Omid Bida from University of Sheffield. Omid, are you here?
Hi, can you hear me?
Yes, and maybe you can go ahead and share your screen.
Sure. So can you see my screen?
Yes.
Cool. Hi, everyone. So I'm Omid, and today I'm going to present some work I've been doing during my PhD at the University of Sheffield involving DAFoam. So it's based around turbulence model augmentation using field inversion machine learning. My presentation has two parts. One's about sensor placement, and the next one is about shape optimization. And I'll go through each in its own section. So the motivations about sensor placement and data-driven turbulence modeling. So we can study turbulence using experiments or CFD, and in both cases, we need to trade off between the level of fidelity we want and the costs. For example, if we're doing experiments, then we're limited by the number of sensors or the equipment costs. And if you're doing simulations, again, it's computational costs. For example, if we're doing DNS, then that will require huge computational resources. A good sort of compromise is to use RANS modeling, which is computationally cheap. We use conservation laws, and then we use a turbulence model to account for the turbulence in the flow. And they're used because they're simple and have relatively low computational costs, but then they're not very accurate for highly complex cases, for example, when we have flow separations. And then here we're interested to see if we can improve the turbulence modeling using limited data that we can actually measure in experiments. So the task is to see if we can a priori determine where to place sensors to then use that for data assimilation. So here's the framework we've come up with for sensor placement. So it involves this technique of eigenspace perturbations, which allow us to create a map of uncertainty in any flow variable. And then we can use that map to guide sensors in location where we have highest uncertainty. And then once we have that sensor placement, we can then perform data assimilation, which is based on the field inversion, which is an adjoint-based data assimilation approach. So the test case I'll be talking about today is we've already seen it in the previous presentation, is the NASA hump case, Reynolds number for around 1 million, and the data I'm using from is from wall-resolved LES. And the flow has separation, so it's difficult for traditional Reynolds models to accurately predict. So how does eigenspace perturbation work? It's a very quick summary of the technique, and then I've given references to if you want to look at more detail. So it's based around the decomposition of the Reynolds stress tensor. So this is the quantity that we're modeling when we're modeling turbulence. And we can decompose it into its components, which is comprised of eigenvectors and eigenvalues. And then we can perturb them using this approach by Carino et al., where it's basically 5 CFD solutions on top of your baseline simulation. In 3 of the simulations, you're perturbing the eigenvalues to their extreme limits. And then in 2 of them, you're perturbing the eigenvectors, again, in their extreme limits, but making sure that it's physically realizable. And then based on those 5 perturbations plus 1 baseline simulations, we can generate an uncertainty map of any quantity. For example, we can look at the streamwise velocity. So here I'm basically plotting a contour of the variance of the streamwise velocity predictions using the 5 perturbations and the baseline model. And we can see that the highest variance uncertainties are in places where the flow separates in the boundary layer, for example, whereas in the kind of free stream away from the hump wall, we have low uncertainty. So now we have this map to use and concentrate our sensors around places where we think it's highly uncertain. Before we do that, I'm just going to show velocity profiles, where in red solid line, we have the black solid line is the LES. Then all the dotted dashed lines are the different perturbations of the eigenvalues and eigenvectors. So we can see that, the biggest spreads and uncertainties are closer to the wall in the boundary layer. So how do we place sensors? So we've come up with this iterative greedy sensor placement algorithm, which is very simple. So we start with placing a sensor in the cell with the highest variance. So we place our sensor, and then we don't want all the sensors to go right next to the same cell, because we're kind of covering that region, and otherwise all the sensors would just go there. So we'll introduce a constraint, which is basically a circle around that cell with an initial radius that we have to specify. And then we exclude all the other cells from potential sites. Then we go to the next highest variance cell, place a sensor, and then create another circle. But this time we're increasing the radius of the circle by the change in the variance. And then we keep going using this kind of relation. And for a specified number of sensors, we can place those sensors to cover the entire domain. So the 2 hyperparameters are the initial radius that we need to somehow fix, and then the number of sensors. These are the details that I'm going to skip, but I'll give you a link to our paper where we show how we can select the initial radius and then the number of sensors as well. A quick going over the adjoint base field inversion, we've already kind of seen it. So it's basically perturbing the transport equation for your turbulence model. In this case, we're using the SST model, so we're perturbing the production term. And then we're solving an optimization problem where we have the streamwise velocity data. We're minimizing the error, and then we're regularizing the problem as well. So it's quite standard. We've already seen this earlier. In terms of key results, so I'm going to compare my results to these different scenarios. So in the left-hand side, we have uniform placement of 33 sensors, kind of equally distant from each other. And then we've randomly selected 33 sensor locations. Then we're using eigenspace perturbations, using two scenarios where in one of them we've used the 33 sensors, in the other one we've reduced it by 10, so using just 3 sensors. And finally, we have the case where we're using all the data available. So here I'm showing the root mean square error reduction for the streamwise and wall normal velocity. So we can see that if we randomly place sensors, then we can't really get any reduction, which kind of makes sense because in these regions here, we don't have any errors really. And then if you use the uniform placement, we have error reduction, but it's not doing as well as when we're using the eigenspace perturbation approach and placing sensor using the algorithm we've shown. And then we can also see that even if we reduce the number of sensors by a factor of 10, with just 3 sensors, we can get much better flow reconstruction compared to the uniform case. Then we can also see that with just 3 sensors, it's kind of comparable to the case where we're using all the data available in terms of the error reduction, which is kind of good news because it says that we can use limited sparse experimental data to perform data assimilation and get good results. Here I'm showing the surface pressure on the hump wall using different scenarios. So using 3 sensors, 5 sensors, and 40 sensors. And we can see that with just 3 sensors, we can get a good agreement with the LES data, especially in the separated shear layer. Again, here I'm showing velocity profiles in the separated region, and we can still see that the improvement with just 3 sensors is quite good. For other cases and sort of the hyperparameters, etc., I will refer you to this paper in Physics of Fluids that we published at the beginning of the year. Okay, so now going to the second part with talking about aerodynamic shape optimization. So the motivation here is that we want to use RANS models to perform aerodynamic shape optimization. And the basic reason for that is that we can't really afford LES or DNS because an aerodynamic shape optimization problem, we need to run a number of CFD simulations. And then it can be very expensive to use higher fidelity approaches. And then we've already seen that the RANS models are not very accurate for separated flows. So we're seeing if we can improve the baseline RANS models and use it for shape optimization even when the flow is separated. So we're going to use the field inversion machine learning approach, which has 2 steps. First part is field inversion, which we've already seen. So that's reconstructing the turbulent flow given some data. And then machine learning is to kind of generalize the field inversion results. So we can use what we've learned for unseen geometries and unseen cases. And then we use that to perform shape optimization. We've chosen a toy problem here based on the available DNS data. So it's parameterized periodic hills. The flow goes from mild separation to massively separated flows, depending on the steepness of the hill. And the data is from DNS. The Reynolds number is 5,500. And we use the geometries, so alpha 0.5, 0.8, 1.2, and 1.5 for training. And then the baseline geometry is for testing. And that's also the geometry that we use for the baseline case of the shape optimization. So a general overview of what I'm going to talk about. So we will have a baseline geometry, and we have a surface that we'll try to optimize. We perform RANS-based shape optimization. We'll use 3 different turbulence models. So the baseline model is the SST, K omega SST. Then we have an augmented version of that using FIML. And then for comparison, we will also use the Wilcox K omega model as well. And then once we have all the optimal shapes from the 3 different turbulence models, we need to verify the flow predictions and kind of quantify the uncertainty or the errors in the predictions. And for that, we use hybrid RANS LES simulations, which I'll talk about in more detail shortly. So field inversion machine learning. So the first part is really we've kind of talked about. So we have the baseline equations, and then we have the transport equation for our turbulence variable. We perturb it in field inversion. We solve an optimization problem, trying to reduce the error in some quantity of interest. And then machine learning is another optimization problem on top of that, where the beta field, the correction field that we had, which is a spatial field, we change it into a function of local flow variables. And we've kind of seen this already in the previous presentations. So the features I'm using are as follows. There's 9 of them. They are non-dimensional, and their scales that are between 0 and 1, or between -0.5 and 0.5. These are quite standard and used in previous papers and previous studies successfully. And then here's the kind of the neural network architecture. So it's a fully connected neural network. We have 9 inputs for 9 features, and then the output is the beta field. We use 10 hidden layers and then 100 neurons per layer. The activation function is hyperbolic tangent, the Adam optimizer, and other details. And here I'm showing the training error for the 4 geometries that we trained on, and the validation is on the case that we left out of training. So quick results for the baseline periodic hill case, starting with the surface friction on the hill wall. So we have the DNS data in black, and then the baseline SST in red. We can see that there's a huge difference between the two, especially the flow reattaches much later in the k-omega SST. But with field inversion and the FIML model, we can improve the predictions. Also, similarly for the streamwise velocity and wall normal velocity, we see huge improvements. And then in terms of the beta field, I'm showing a case where I've actually performed field inversion using the available DNS data, which is this contour here. And then this one is based on the neural network predictions. We can see that they're kind of broadly similar, but they have the field inversion was much smoother. However, we can see that it doesn't really affect the overall predictions of the quantities that we're interested in too much. So we can still use it for other cases. So the IDDS, a quick sort of info about how we perform that. So we use the Spalart-Elmaras turbulence model with the IDDS, and then I actually perform IDDS for all the parameterized geometries. We have 2 different meshes depending on the steepness of the hill. So it can be from 2.5 million cells up to 7 million cells. Here are the boundary conditions, and here I'm just showing a Q criterion plot for the baseline geometry. So verifying the IDDS result for the baseline geometry against the available DNS, I'm showing on the top row the streamwise velocity along the periodic hill geometry, and then in the bottom the wall normal velocity. We can see that they're quite well matched. Similarly, for the Reynolds stresses, the normal and shear Reynolds stresses, we have a very good match between the IDDS and the reference DNS data. So then that makes it that lets us to now use the same kind of setup to verify our optimal shapes, the flow predictions for our optimal shapes. I will also show that drag coefficient on the hill wall using the IDDS for the various geometries alpha. And then we have the different RANS models. So we have the baseline SST, the Wilcox k-omega, and the field inversion machine learning augmented SST. We can see that the baseline one massively underpredicts the drag compared to the IDDS, whereas if we use the augmented version of that, we get results that are closer to the IDDS. And then we can see that the K omega is also close to the IDDS, so meaning it's a bit more accurate than the SST model. So why do we care about the drag coefficient? Let's go and talk about the shape optimization. So it's kind of a proof of concept case, really. This is more of a mathematical construct, this optimization problem, but basically we're trying to reduce the drag on the hill walls, the lower hill wall, and then we have some constraints. So the constraints are in terms of the geometry, so the maximum amount it can be deformed. We have prescribed pressure gradient because the flow needs to be driven by something. So we need to get a bulk velocity. And then we have another constraint about the turbulence variables to ensure kind of the flow is very turbulent, otherwise the optimizer will tend to just turn this into a channel, in which case we remove all separation in the flow. So some key results. So we'll have 3 different models. We have the baseline SST in red, we have the augmented SST in green, and then we have the K omega in blue. The dashed lines are the baseline geometry, and then the optimals are in the solid lines. We can see that the baseline SST model, we can only reduce the error by 4.5% if we get this shape. And then if we use we can also, I'm also showing the change in drag based on the IDDS predictions of these 2 geometries. And in this case, they're the same value, so 4.5% reduction in error. But if we use the augmented SST model, we'll get a totally different shape and much more error reduction. So based on the RANS predictions, we have a reduction of about 27%. And based on the IDDS predictions of these 2 geometries, we have a 25% reduction. And we can see that the reductions are kind of similar because the flow predictions are similar in these 2 cases, even though one is RANS simulations, one is IDDS. And then in terms of K omega, again, we can see that based on the RANS predictions, we reduce the error by 28%. And then if we perform IDS for the same shapes, we see that the change is around 20% in the error, in the drag. Some more sort of comparison of the error in the predictions of the baseline geometry and then optimized geometry. So I'm comparing the 3 different optimization cases with the 3 different turbulence models, and I'm showing the RANS predictions for the baseline geometries. So we can see that the SST model is very inaccurate, so the error is about 30%, and then the augmented models has much lower error, and the K omega has also a lower error. And then this part is for the optimized shapes, and again with the error in the drag prediction for the optimal shape for the SST is 30%. So this is comparing the IDDS and the RANS values, whereas it's 9% for the augmented SST and 13% for the K omega. So we can see that the lowest error is with the augmented model. Showing the surface friction on the hill walls, similar story. So we have huge errors for the baseline SST model, whereas the errors are minimal for the augmented SST and then the Wilcox K omega. And here I'm showing the surface pressures. Again, the baseline SST is quite inaccurate here, and the augmented SST and the Wilcox K omega are much better, although there are some discrepancies. So maybe for the training, we only use streamwise velocity data, but if we combine that with surface pressure, then I think we can improve this even more in terms of the surface pressure predictions, but also in terms of the drag coefficient predictions, because the biggest component in that is the pressure drag. More comparison between the IDDS and the baseline RANS models. So here I'm showing the streamwise velocities for the 3 different models and 3 different optimized shapes. We can again see that the baseline K omega SST is very inaccurate. So it has a much bigger flow separation compared to the IDDS of the same shape. But we have very good agreement for the augmented SST model, and similarly for the Wilcox K omega. So here's a quick summary of the 2 parts of the presentation. In terms of the sensor placement, we used eigenspace perturbations to create an uncertainty map, and then we used that map to place sensors in regions of highest uncertainty. The advantages of the approach is that it's a priori, so we don't need to do data assimilation while we're placing sensors. So you place the sensors and then you do data assimilation. It has relatively low computational cost compared to other methods in literature, and the good part is that it's kind of tailored to the primary source of uncertainty in RANS models, which is the Reynolds stress tensor. So we're actually basing our sensor placement strategy knowing the uncertainties in the Reynolds stress tensor predictions. In terms of the shape optimization, we've enhanced the SST model using field inversion machine learning. Forming shape optimization, we saw that we can get an error reduction of about 25 to 27% using the augmented model compared to the 4.5% with the baseline. And even in the 2 cases, when we compare the RANS and IDDS predictions, we can see that the baseline SST is very inaccurate. So we can't really trust even this 4.5% reduction. And then we also showed that the turbulence model does affect the outcome of the aerodynamic shape optimization, because we had the Wilcox K omega producing a totally different shape to the SST and the FIML model. With that, my presentation is over, so I'll take any questions. Thank you.
Thanks, Amit, and very nice presentation. Any questions from the audience?
Hi, am I audible?
Yep.
Yeah, we can hear you.
Yeah. I have a question on the correction term distribution of the periodic hues. I mean, it's like the page 15 or something, that the figure shows the distribution of the correction term in the periodic hues. I can't remember the exact page number. Oh, yes, it's here. Yeah, I think the distribution is not quite smooth. So I think would you consider using some the normalization, that's using some normalization will help in this case. In fact, when I'm doing the field inversion, I also found that if I do it on the periodic hues, the correction term may not be that smooth. Yeah.
I mean, we haven't really looked into trying to make it smooth. I mean, part of the reason that it's not smooth is because when we're doing field inversion, the beta field is frozen during the CFD simulation. And it's once it converges, then it's kind of makes it even smoother during the optimization. And it's fixed, but when we're doing using the neural network to do the CFD simulation, the beta field is actually predicted for every iteration. So that can be part of the reason that it's not very smooth. But the key thing to remember here is that the fact that it's not very smooth doesn't really affect the predictions of the quantities of interest, which we've shown here. But I mean, it
yes.
might be interesting to look into, making it smoother and how that affects.
Yes, of course. But maybe making it smoother maybe can, increase the generalizability of your model or something. Maybe something like that. Yeah.
Maybe.
Yeah, I'm not sure. I'm just doing some suggestions. Yeah, thank you.
Cool.
Thank you for your
Thanks.
answer. Yeah.
Other questions?
Hi, Amit. I'm audible?
Yeah, we can hear you.
Yeah, hi. Thanks for the really interesting presentation. So my question is regards to the ASO. So when you're doing optimization, I'm assuming before training neural network, you might have done some parameterization. I'm interested to know what type of parameterizations did you use and how did you train the neural network? What are the parameters you train the neural network between? Is it between the changes in the geometry with respect to the fluid parameters or other sort of methods you might have used?
Oh, so for the neural network training, it's kind of decoupled from the shape optimization part. So we have the four geometries that we use for training. So it's parameterized from the DNS dataset that's available publicly. So because it was available, we started with this. We perform field inversion, and for machine learning, we use the non-dimensional flow features, which I showed here, the 9 inputs. So those are the neural network inputs, and then the output is the beta field. And then once we have trained the neural network, we then use that, the pre-trained neural network, in the aerodynamic shape optimization.
Okay, so how do you reconstruct the flow field?
Reconstructing the flow field is so that's again part of the FIML approach. So reconstruction is done during the field inversion part. So where we're solving this kind of optimization problem. So we will have one particular geometry, one of the periodic Hill shapes. We have the beta field that we're optimizing, and then we have the data from TNS in the objective function. So that's when we're doing flow reconstruction. And then we're doing multiple of those for the different geometries, then using neural networks to generalize it.
All right. Thank you.
I have a question about your first part about the sensor placement on it. My question is general, is how this approach can be used. Say, for example, I want to use your approach. Do I need to have the access to my source code, or it's a complete post process when you do the eigen value perturbation?
Oh, so yep, I didn't talk about that. But so the eigenspace perturbations is in SU2. So it's open source available in SU2. So I do the eigenspace perturbation simulations in SU2 using the same mesh and kind of the same setup. So we're assuming that SU2 and OpenFOAM will be very similar. So we're neglecting any kind of differences between the two different models in the two different software suites. And then I'll compute the variance, and then when I'm doing data assimilation, I'm doing it in DAFoam.
Gotcha. So I guess we can't just directly reuse. We basically it's this eigenvalue perturbation is a module built in SU2.
Yeah.
Okay, so gotcha. So if you want to move this capability to DAFoam, we might need to look at the source code, somehow move it there. It's not like a pure post-processing process, meaning that we just read some velocity pressure fields into the memory, and then we can call some eigenvalue perturbation stuff. It's not like that.
No. So it's actually part of the CFD simulation because you're changing your turbulence model during the simulations.
Gotcha. Yep, that's my question. Thank you.
Thanks.
Any other questions before we go to the next presenter? Okay. I guess no more questions. Thank you, Amit. Okay, our next presentation is from Uttam Padmanabhan. He's from University of Southampton. And Uttam, are you there?
Yes, hi.
Great. Maybe we can please go ahead. Yeah.
Yeah, let me just try to share my screen. Is it visible?
Yes. We can
Yeah,
see
awesome.
Yeah, but it says University of Southampton, but we cannot
Yeah,
see.
that's fine. That's fine.
Fine.
Okay.
Right.
Yeah.
Okay.
Just wanted to make sure
Yeah.
it's working and fine. Okay, so good morning, evening, afternoon to everyone, depending on where you are in the world right now. So I will be speaking about data assimilation of turbulent flows in stalled airfoils today. So to give you a bit of context, I'm a second year PhD student at the University of Southampton, and I'm advised by Dr. Sean Simon and Professor Bharatram Ganapati Subramanian. So I just want to go through the introduction and what we'll be looking at today in this presentation. So I will start with the motivation for why we are doing this and touch upon a little aspects of airfoil stall. This will be followed by aims and objectives of what we set in the study. These aims and objectives are not exclusively restricted to the work that has been completed, but also extends to the work that is currently being done, of which I would give you some insight into what's happening in this space at the moment as we speak. I want to go a little bit into variational data assimilation. I'm sure since everyone uses DAFoam here, they understand this to a good degree. But just to sort of go through those equations once to show what we are really doing and how it is relevant to this talk today, and a little introduction about the computational framework that we are using for this particular study. I'll show you some results about the stalled airfoils that we have tested this framework. This will be particularly using experimental data at different Reynolds numbers. So you get a good understanding of what really can be done. We kind of pushed DAFoam to the limit in terms of what it can do for data assimilation of stalled airfoils or separated flows in general, and we'll be showing you a little bit about that. And of course, I want to conclude with some of the future work that we have in plan, and also something that we are working on. And of course, would love insights and questions and ideas from all of you as we go along. Right. So we know that airfoil stall is an extremely complex flow behavior, not just in 2D but in 3D as well, with the presence of stall cells and so on. So it's particularly challenging to model these stalled airfoils using low fidelity models such as Rand's turbulence models. When we look at experiments, performing experiments at high Reynolds numbers is challenging. And here I show a setup from that one of my colleagues had used as part of his work, where you have multiple lasers to illuminate both sides of the airfoil. So I noticed that a lot of the researchers here use high fidelity data. So just for to sort of take a detour into the experimental world, it's particularly challenging to capture even some very basic aspects of stalled airfoils. So this setup here is that you see is from a particle image velocimetry or PIV setup, which requires two lasers. And one of the major issues that experimentalists face is the distortion of these images and having to stitch multiple images together to increase the field of view. Right. So experiments, of course, they are really useful to understanding the flow physics, but they also come with a set of challenges, and not everybody has access to perform the experiments of high quality. Right. And additionally, secondary quantities such as forces, for example, require separate hardware. It's notoriously difficult to measure quantities like wall shear stress, which we can get easily from computational models, right? So these are some of the issues that experimentalists face. And if we look at the other side, that's Rand's turbulence models, as I mentioned, they are very cheap and they can be used extensively with minimal setup and expertise. But we also see that they have quite poor accuracy when it comes to some basic cases, which most of you have spoken about today with the periodic hill, for example. The one that I show here is just comparing the DNS and the baseline case that is performed using a Spallard-Ulmerus turbulence model. So from this, we gather information which we probably already know, but just as a refresher, that Rand's turbulence models are inaccurate, but then they offer a cheap alternative to study complex flows such as airfoil stall. And experiments, on the other hand, give a good picture of the flow physics, but then they are lacking in terms of the imperfections and also experimental uncertainties and errors in measurement and so on. So really going forward, we use this as a springboard to set the aims and objectives of the study, which is to improve the prediction of Rand's turbulence models. And we do this by incorporating experimental measurements and using data assimilation. A sort of added benefit as we go along the way is that we reduce experimental uncertainty and noise, which is prevalent in experimental setups, especially for higher Reynolds numbers flows and flows with strong separation, as in the case of stalled airfoils. As I mentioned, the aims also includes elements that we are still working on, and we are looking to work or sort of develop an algebraic model using sparse symbolic regression. I noticed that there was already a presentation about symbolic regression, so it was really nice to see that the work that we're doing is sort of relevant in this space. And with that, I want to go a little bit into data assimilation. So we know that the variational method minimizes discrepancy between a model output and observations, and it does so by tuning some control variable or a design variable. Here you see a simple objective function which has a high fidelity data as Q tilde and model output as Q, for example. Now, just to give a little bit of understanding of what the state of the art is in variational data assimilation. So most of them employ the continuous adjoint. Now, I don't have to spell out the advantages of a discrete adjoint because that's pretty much the reason why most of us are using DAFoam. So, but in the data assimilation community, most of the work started with continuous adjoint. The seminal work by Forrest, for example, in 2014, started off with the continuous adjoint formulation, which in fact is still used till date, actually. So it was quite a remarkable, thing back in 2014. But of course, now we are looking at more complex cases. So the question still remains that, okay, is continuous adjoint really the way to go forward? And as you know, it has a bunch of disadvantages, such as having to derive new equations for each turbulence model, and handling complex 3D geometries is a challenge because of these simplifications that are used to derive the adjoint equations for different turbulence models. And there's no real unified framework, as is in the case of DAFoam, which is a trouble if you're looking to study complex 3D cases, for example. There are a few studies that use discrete adjoint methods for data assimilation, but they're approximate. In fact, one of the first ones that came out was the work by Oliver Brenner, the ETH group, which they use a sort of an analytical method, but they also add some approximations. And here you can really see that there are some issues in terms of the accuracy when compared with the finite difference approximation. And one of the most important things, which forms the focus of my work, is that the use of experimental data is very minimal. My advisor actually was one of the first to use experimental data in variational data assimilation. And of course, now more and more studies are coming out. So it's important to sort of start looking at this from the lens of experimentalists, because going forward, more and more people are starting to do experiments, and more data sets are available, and the need for data assimilation is more now than ever, right? So with this, I want to move on. And of course, 3D data assimilation is still a very new area of research, and not many people are investigating into this as we speak. So variational data assimilation, just going into the math a little bit, we formulate an objective function. We can use velocities, pressure, really any state variable. And in this study, we use forcing term in the momentum equation because the literature has shown that this provides a good way of correcting the turbulence models, especially for strongly separated flows. So this is going to be our control variable. And we solve an optimization problem, which we're all aware of, subject to a set of constraints, which are the Navier-Stokes equations, or the Rance equations in this case. And this discrete adjoint part, where to get the sensitivities, we use DAFoam, which is like a big benefit, or it's quite ahead in terms of what the others are doing at the moment. And using these sensitivities, we update the design variable, and then this process goes on until we get an optimum momentum forcing, which reduces the discrepancy between our experiments and our model output. Now, we have done a few implementations in DAFoam, not particularly in the area of the methods, but in the area of processing, because since the use of high fidelity data such as DNS or LES, you can perform an interpolation and get your reference data onto your Rance grid. But when it comes to experiments, that's not always possible. And that's because we are required to calculate this objective function on the experimental grid so that we don't modify this experimental data because it has uncertainties, and these uncertainties propagate as you interpolate it onto different grids, for example. And also, experimental data is not always very well resolved. So having to interpolate them onto a Rance grid, for example, you would have to super sample it, which is not really a desirable thing to do. And in DAFoam, we made two implementations to handle these discrepancies in the grid topologies. And we do that by performing a cell-weighted volume averaging. And this is, of course, quite flexible because it can also be applied to 3D data assimilation cases, which is what we are looking to do going forward. So for the cell volume intersected case, we consider the intersections between a computational grid and an experimental grid. Here you see the experimental grid shown in dashed lines, and the computational grid is in the solid lines. The goal is to really use all the information from the CFD and arrive at a cell volume averaged velocity, which is then going to be used to compute the objective function. So this was one of the implementations that we did. And the second one is we decided to simplify it a little bit and not consider cell volume intersections, but instead just used simple cell centers to inform the calculation of our cell volume averaged velocity. So with this, we can use experimental data, which is on a uniform grid. The output from a PIV is typically on a structured Cartesian grid, whereas our CFD is of course stretched and pulled, and it's not really uniform. So we can use this implementation to calculate our objective function, and going forward, compute sensitivities and perform the optimization step. Right. So coming to the cases that we'll be looking at today, we have performed the assimilation for the 0018 airfoil at 10-degree angle of attack and a Reynolds number of 10,000. This is a fairly simple case, which in fact the assimilated cases are in literature. So we just wanted to use it as a validation step. I won't be showing results from this, but this is one of the cases that we tested. We pushed it a little further, went to a higher Reynolds number case of 70,000 at 15-degree angle of attack, which displays deep stall characteristics. So it's a bit of a complicated case for the assimilation, and it was quite interesting to see how it performed. And we pushed it even further for Reynolds number of 400,000, which is typically the range of microaerial vehicles, if for those of you who are interested in that area of application. And we've done a lot of work in case of the flexible and rigid wings at these Reynolds numbers. So we wanted to test how the variational method also applied for data assimilation for this high Reynolds number case. And in all cases, we are performing, of course, a steady state assimilation. We're using mean fields as our input data from experiments, typically from particle image velocimetry. And we are performing the momentum source correction, the correction term that's in the momentum equations. Just to sort of give you a visual representation of what it looks like. So we have the computational grid in black, and we have the experimental domain, or the field of view, as they say it, restricted to the region represented by the red box. So you can already see here that the field of view is limited, particularly closer to the airfoil, whereas for a computational domain, you would want to have a larger domain so that you don't have the influence of boundary conditions on the regions close to the airfoil. Right, going forward, we have the first case, which is the Reynolds number case at 70,000 for the 0012 airfoil. These are some of the results. These are, you're looking at the mean fields, the first row showing the streamwise velocity, and the second row of images showing the wall normal velocity component. And the first column being the experimental, the second one is the baseline from the Spalart-Armras turbulence model, and the third one is the assimilated field using the momentum correction. So it's quite evident that these improvements are quite significant, and that, of course, as we know, the Spalart-Armras turbulence model is not very good at capturing these flow physics, especially for stalled airfoils. And an interesting thing that we also noticed is that when we looked at the secondary quantities, the quantities that are not directly assimilated, we saw that there was also an improvement in the pressure, in the surface pressure. So the surface pressure from the experiments is denoted as a black dashed line, and the one from assimilated is in the blue line. So we see that there is, of course, a reduction in the suction peak when compared to the baseline case, which also improves the prediction of lift coefficient. And all these were positive outcomes that we were observing, which, in fact, in previous literature, people usually struggled with the pressure aspect in variational data assimilation. And we noticed that this was happening quite well, and this was an interesting thing to note. And of course, this positively affected the lift coefficient as well, and the assimilated case was able to improve on the baseline and is within about 4 to 5% of the experiment. Now, this ties quite well with the objectives that was mentioned before, where we require additional hardware to capture or to compute some secondary quantities. And in this case, you would require a load cell from an experiment to get the lift coefficient, which we noticed can be obtained just by performing an assimilation and not even including any data from the wall. So the next thing that we looked at was, is the assimilation performing well outside the region of the experimental field of view? So the experimental field of view in this, so these are the wake deficit profiles in the wake of the airfoil. So you notice here that the data is available only up to the point where you see the black dashed lines. I know it's quite faint, but you can really see that it stops after the third profile. And we notice that the effect of the assimilation carries forward downstream. And this is a positive result from the perspective of resolvent analysis, where it's important to have correct wake deficit profiles if you are going to use the mean velocity fields for performing resolvent analysis. So this was also a positive outcome that we observed. Of course, for those of you who like to see numbers, we got a relative error of an improvement of 86%, which is quite good. And also, we looked at the forcing fields. Now, I don't want to go too much into the detail of the math, but the forcing field can be decomposed into a solenoidal component and a rotational component. And we take the curl of the forcing field to remove the influence of this rotational component, just so that we can compare it more accurately with our experimental data. And if you see here the assimilated case, of course, the baseline case is quite far off. This forcing really shows you, or rather explains, the reduced size of the wake. And the assimilated fields look a lot better compared to the experiment. This sort of pattern that you see here is because of the noise in the experiments, which is handled quite well by the assimilated profile. So this is beneficial for those looking to do some sort of machine learning applications for regressing the Reynolds stress term. So this shows that it's quite well matched with the experiment. So going forward, we looked at the 400,000 Reynolds number case, which of course, I'm just going to show the mean fields. The important thing to keep in mind here is these distortions in the experimental data that you see here in the form that can be observed in these contours. This was because of the simultaneous overlap of the two laser sheets, which then had to be filtered and processed, but still it does have the signature of this experimental error or noise, as you would say. And we can see that assimilation is able to sort of smooth these things out in addition to improving the prediction of the wake, and also sort of smoothing out these distortions that are a result of errors when performing the experiment. And for this Reynolds number case, we of course looked at various other quantities, and these are experiments that are performed by my colleague Craig Thompson, who also has published these results, and I'm happy to direct you to that if you're interested in giving it a read. I want to discuss a little bit about the forcing field. Now, the forcing field that we observed for both the Reynolds number cases, the top row being the moderate Reynolds number and the bottom being the high Reynolds number cases, we noticed, of course, some similarities in the forcing field. And needless to say, all the variables have been normalized to 1. The chord has been normalized to 1. The velocity field, the inlet velocity has been normalized to 1. So really the only difference between these two Reynolds number cases is the kinematic viscosity. And we sort of hypothesized that could there be a sort of a universal scaled forcing field which can be applied to different Reynolds numbers of the same profile and for the same airfoil, and for the same angle of attack. And this is something that we are kind of looking into right now and would massively help in design of experiments. It would reduce the number of experiments to be performed, parametric studies to be performed for experiments, because it's not it's quite an expensive affair to perform even something as simple as a Reynolds number sweep for experiments. So this really shows the areas where the forcing is attacking, which is typically in the shear layer, which is also where majority of the differences between the Rand's turbulence model output and the experiments exist. So it was good to see that the forcing is being applied locally here, and it's what is improving the mean velocity field prediction, and not that it's being applied elsewhere and it's having sort of like a downstream effect. So this was something that we are working on at the moment. And another thing which we tried to do, I wouldn't say if we were entirely successful, was to quantify and use the experimental uncertainty in our assimilation process. So if you see here, these are the absolute and not relative, the absolute uncertainty fields for the moderate Reynolds number case, the left one being the streamwise uncertainty and the right image being the wall normal uncertainty. So we just used a very simple method where we computed the norm of the output velocity field with respect to the experimental data, and try to ensure that this was within the bounds of the experimental uncertainty. And to sort of show you graphically what I mean, so this is just a convergence plot of the L1 norm for this optimization case. And the dashed line that you see is the cumulative experimental uncertainty from the streamwise and the wall normal cases. And we sort of put forward a framework that, okay, if the extent of improvement of L1 norm is below this dashed line, then that's where you start seeing some overfitting that the simulation is doing. So it's useful to make sure that this does not reach that limit. And as you see, that's really what is happening. But then there are also different caveats to this, that we have not quantified all the uncertainties. These uncertainties are just in the uncertainty in the subpixel interpolation. So there are other sources of uncertainty that we have not taken into consideration, but this is just a framework that we proposed, seeing as more and more people are starting to use experimental data in the data assimilation process. Going forward, I did mention that I will speak a little bit about the sparse symbolic regression. This is actually something that we are working on with TU Delft, the group that's headed by Dr. Richard White. And they use this tool called Sparta. And the methodology is fairly, for those of you who do symbolic regression, it's fairly simple to follow. But I won't go too much into the details of it. I've attached a link there for the source, and it's quite a good read. So those of you really interested in the sparse symbolic regression using Sparta can refer to that. But really, what they do is they use high fidelity data and solve for omega and nu-t. So this is like a frozen approach. They do not update it, but they just get the omega and nu-t fields, and use this to get the residual correction terms. There is the anisotropic correction term Bij, and the R is the correction term in the production equation of the turbulent kinetic energy. And finally, they do the regression. They regress models for these correction terms, which is what they have been doing so far. But what we wanted to do was we want to use our forcing that we get from data assimilation and try to regress the forcing as opposed to regressing terms in the turbulent transport equation. So originally Sparta, what they've been doing so far is using high fidelity data and regressing the turbulence anisotropy and the production term in the turbulent kinetic energy. But now we have proposed that, okay, let's try to regress the Reynolds force vector or the forcing in the momentum equations to try and get a simplified algebraic model for airfoil stall, 2D airfoil stall. So this is something that is a work in progress. And yeah, if you're interested, we can speak about it, and more of it will be coming soon. So you will find out about it. And another thing that's in works is the 3D data assimilation case, where this is a simple case of a wall surface mounted cube, which is in fact a tutorial on OpenFOAM. So we generated some high fidelity data using detached steady simulation, and we generated a bunch of mean fields using this test case. And we wanted to see if it was possible to use single plane measurements to reconstruct the entire field. Now, the application of this, which you might have realized, is since we want to use PIV data, which is typically from planar PIV or even stereo PIV, would just be on a single plane with multiple planes that is used to image the flow field. We wanted to test if it is even possible using a single plane to reconstruct the entire field before having to go into the wind tunnel and perform an experiment. So we use this as a test case to do that. The green line that you see there is the wall normals, the spanwise wall normal plane, or the spanwise plane, which has 3 components of velocity, which is used as reference. And with this, we use the data assimilation framework and try to reconstruct the entire field. I'm just going to show some preliminary results. Of course, this is still a work in progress. So you see the dashed, the solid contours are from RANS simulation using the SA model. And the solid contours that you see are from the high fidelity detached steady simulation case. These are, of course, mean velocity fields in the streamwise and the wall normal planes. Now, when we performed the assimilation using the spanwise plane, we observed that it's able to make corrections in planes that are not only restricted to the one where we provide data. So we provide data on a spanwise plane, but then you see here that there are improvements in the wall normal and streamwise planes, which we just used as a canonical case to apply to future problems. So this was quite promising, and we are right now trying to work with limited PIV data and perform the same exercise that we did for this canonical surface mounted cube case. And with that, I just want to conclude a few things that we discussed. I know it was quite a lot of different things, but maybe we can try to summarize it in a concise way. So we, of course, made this implementation for handling topologically dissimilar grids, experimental and computational grids, and we've also implemented it, tested. We also actually recently published with this the data that we did use with this implementation. So it's open access and it's available. And if you're interested, please do drop a message and I can share it with you. You can also have a discussion. I'm happy to help. We observed that the momentum forcing in the Rand's turbulence model equations really helps with modeling of stalled airfoils. Now, a lot of researchers before have tried canonical cases, have tried turbulence model corrections, which are good. But then when we try to apply the same thing for higher Reynolds number stalled airfoil cases, we observed that it's not really as straightforward, and the improvements in the predictions were not that great. So seeing as data-driven turbulence modeling is beneficial for those who do not have really an expertise in the physics, in actual physical modeling, we wanted to sort of come out with some framework which can be easily used. And seeing as how a DAFoam is helpful in that sense, we try to just merge this forcing in the momentum equations with the discrete adjoint tool DAFoam, and we saw that okay, these are giving us quite good results for higher Reynolds number cases, and currently it's being tested for 3D. They also improve prediction of reconstructed quantities. This is quite important, especially if you speak to an experimentalist. They'll tell you how difficult it is to measure 10 different quantities with 10 different setups and apparatus. So this is beneficial significantly for the experimental community. As future work, we have planned the symbolic regression. So we have a bunch of cases with a Reynolds number sweep. We have an angle of attack sweep. We also have different profiles, which we will be using to try and symbolically regress and come out with a simple algebraic model for the case of stalled airfoils. And of course, we're also working on some limited observational data for 3D flows, especially the ones with a wake generator and with 3D stall in the case of stalled cells. So this is a work in progress. And yeah, that's the end of the presentation, and I'm happy to take questions.
All right, thanks, Udan. Any questions from the audience?
Yes, I have a question.
Yeah, please go ahead.
So the correction field in your work was a source term in the momentum equation?
That is right, yeah.
So you weren't using any turbulence model, just the momentum equations, right?
So a turbulence model is in fact used. Let me just go back to the equation, and perhaps we can quickly take a look. Yeah, so here, if you see here, let me just get a laser pointer. So this correction term that you see here is the one that we're optimizing, but that's a corrective forcing. But there's also a Reynolds forcing here, for which we use a turbulence model.
Okay, I get it. Okay, so is it similar to a field inversion, but you just use the source term directly as a corrective field?
That's correct. So in a field inversion case, you would just you would find the scalar field, which is the multiplier to say the production term, right? You find the beta field, but in this case, you are finding a momentum or a vector field as opposed to a scalar field.
Okay. Okay. Thank you.
Yeah. Any other questions?
I do have a quick question in terms of adding this FCI, this force in turn, into the momentum equations. In a slide you showed that the range of the force in turn is -3 to 3. You also mentioned you somehow normalize things such that, because I would imagine that this force in turn the range of this force in turn will be very different depending on which case you run, depending on the velocity magnitude, depending on the geometry and such. And how do you normalize it such that it's within a small range? Is this -3 to 3 the upper and lower bounds you prescribe when you do the field immersion optimization? Do you need to prescribe bounds in order to make it work?
Yeah, so that's a very good question, actually. So this is something we thought about quite extensively. So to answer the first part of the question, which is how do you normalize this? So this is more of a hypothesis rather than something which we have, which I can tell you definitely. But another colleague of mine was working on the similar problem, but using a different method. He was using a state observer method. And he tested a case for which none of the quantities were normalized. So he did not normalize the chord, he didn't normalize the velocity. He used all dimensional quantities. And he noticed that the scaling of the forcing was in terms of inertial quantities, which is the free stream velocity and the chord length. So if you consider this to be an acceleration term, which is made of a second square, you can use a combination of the free stream velocity and the chord length to normalize this forcing. But since in my case, I have already normalized the forcing to start the problem, so I've normalized the chord and I've normalized the free stream velocity, we think that this is already a normalized forcing and does not require further normalizing, if that makes sense.
Yeah, sounds good.
So the second part of the question is the bounds. Now we do set these bounds to be -3 to 3. And the setting of the bounds is again something which we did think about quite a bit. But it is, again, the bounds are, again, in this case, a hyperparameter. And we notice that it needs to be of order 1 if you are scaling all the quantities to 1. So when we set it to we started with a -1 and 1, -2 and 2, and then checked -3 and 3. -3 and 3 obtained good convergence and did not blow up the solver. So we decided that, okay, -3 and 3 is a good range. Now, if we have already scaled all the quantities, and if we set a range for this forcing for one case, it's the same range is also applicable to different cases, provided they are also scaled quantities of free stream velocity and chord length. So as long as you're scaling everything to 1, you can use these bounds to be of order 1.
Okay, that sounds good. Yeah.
Yeah, because we did struggle quite a bit with this. It's extremely sensitive to the bounds because it's a vector field. So it's like 3 components as opposed to 1 in the case of field inversion. And I know that a lot of people in the machine learning community would favor dimensionless scalar fields as opposed to, say, dimensioned vector fields in terms of having to regress it. But we are also trying some regularization methods. Like we're trying a smoothing regularization, the gradient of f. We're taking a norm of that. And these are still some things that we're trying to make it a little more robust so that you don't have to try different hyperparameters for the bounds of the forcing.
Okay, sounds good. It's very good to see that you're using a different approach than many others who are doing fair machine learning. Okay, any other questions from the audience?
One quick question.
Yeah.
So have you tried just using the sort of standard field inversion sort of formulation for data assimilation and comparing that to the way you're doing it with the forcing term and see if there's any major differences in terms of the final flow reconstruction?
Yeah, that's a very good question. I think I, in fact, started off with the field inversion. So my first attempt was I started off with a simple canonical case of the periodic hill. That was also when I was in touch with you. So we started off with that. And for the airfoil cases, we started the field inversion. But then it's either I'm not doing it correctly or it's not possible because we tried almost everything and nothing could give anything remotely close to what we're getting with the momentum correction. And by remotely close, I mean it was not even like, it was almost negligible changes. So either I'm doing something wrong, which if maybe if someone could point out, I'd be very happy. But we tried it for a significant amount of time before switching to the momentum correction. So
it's the data that you're using publicly available to try it using standard field
I think the one with the 70,000 Reynolds number that's published in AIAA journal, and that is, let me just take you to the references. That's this one. This one is like publicly available, or I would say it's available on request. So if you request it, I'm sure the authors would not have an issue releasing it. So maybe you can give it a try. I mean, I tried the field inversion case and also a source term in the turbulence transport equation for the spa-terminus turbulence model. In fact, I also tried the K omega SST turbulence model, and both cases I could not get good improvement. So we just sort of ruled it out, saying it's possible that it's an artifact of the experimental data as such, and not the method itself. So,
Right.
so yeah, you were saying something?
Okay, just to check which optimizer were you using? Were you using IPOpt?
I was using SNOpt.
SNOpt, okay. Okay.
Because I believe you can't, I think Ping had told me that, I mean, I was using IPOpt to start with, but for some reason, IPOpt does not seem to work with the momentum correction. So I switched to SNOpt, and it was fine. So
Yeah, sometimes SNOpt performs better than IPOpt, but yeah.
yeah, I've had lesser sleepless nights, shall we say, once I switched to SNOpt from IPOpt. So yeah, we transitioned completely to SNOpt. So we use only that.
All right, I guess we have to move on to the next topic. And thanks, Wutan, for your presentation.
No problem. Thank you so much, everyone.
Okay, let me share my screen. I have our next topic is to promote a more interactive community. And we have about 45 minutes to have a free discussion. So, but before that, let me talk a little bit about the backgrounds, where we are at right now. This slide shows you the DAFoam usage. The plots on the right-hand side is the number of papers published that use DAFoam in their study. And we have in total of 46 papers published, including journal papers, conference papers, as of today. And the red curve is the total paper, and the blue curve here, dashed curve, is what we call independent paper, meaning that the ISU and University of Michigan teams are not co-authors. And we are very glad to see that almost 50% of them are independent. And very glad to hear that this is useful for your research. One thing I want to highlight is that if you use DAFoam, make sure that you mention the name DAFoam in your paper, because I believe most of you have already been doing this, but we saw some papers that mention, we use this approach. It looks like DAFoam, but they didn't mention the name DAFoam in it. Then that's sometimes hard to see whether I use DAFoam or not, but just want to highlight this. What's next is I want to talk about some current interactions I have, the approaches. And right now we have three main ways to interact with users and developers. And the main approach we use right now is through the GitHub discussions. Chen, you mentioned that people ask questions and we will answer questions. Yeah, this is a preferred way to interact with the developer teams and all other users, because that maybe your questions could be useful for some other users. And for example, if you look at the right-hand side, this is the plots of number of questions answered on GitHub discussions. We opened this feature in late 2020. And then last year, we had about 90 plus questions. We answered all of them. As of today, we have already 60 plus questions. So I'm very glad to see that this is a very interactive platform, and hopefully it's useful for you. So in terms of the second way, sometimes people write me emails and asking, hey, this is not working, and this is okay too, but I still prefer the user discussion because some of the questions are of general interest. A third way we can interact is through this workshop, but this workshop is not happening very frequently. I can do that maybe once per year, something like that. But it's still a way to interact, especially it's good if you want to present something, that the workshop is a better way. In terms of the questions, most of the questions about how to use DAFoam, maybe they have a bug and it's not working. And some of the questions about how to develop a new feature or a new capabilities. And I believe that the GitHub missions, we have some, maybe can, Yeah. Let me mute. Make sure everybody's mute. I believe that GitHub discussions and can fix the potential bugs. If you see bugs, usually we will fix them very quickly. And then if you have a question using that, we'll say, for example, I run your tutorials, I get an error, and we usually can fix that. But for the third one, so somebody asked, for example, we got quite a few questions and requests saying that, can you add the missing plant boundary condition to enable multi-stage turbo machinery simulation and optimization, this capability. And this is something I want to focus on today. So how do we make it more interactive such that if you want a new feature, it can be somehow implemented? Okay, that's what we want to discuss today. So I'm going to first talk about my proposed approach, then we will have a free discussion and what's a better way to promote this more interactive community. So I want to propose that people use this feature requests, this approach, and you can create an issue to ask for new features. If you go to the DAFoam repository, if you click issues, create an issue, it will ask you that it's a bug or it's a feature request. You can select a feature request, and then you will see a templates and what is feature, what do you want, and can you provide a case or what's the expected behavior, something like that. Once we see this issue, then we will do, of course, we will first review these requests, and then we have two ways to implement it. First is that we will develop teams will, and for example, I can add these new features. And this scenario one usually is a very quick fix. For example, can you write the adjoint vector to the disk? Can you write the default FFD points? This kind of features, then we can usually add it very quickly. And a second scenario, if this feature is like more, it involves more developments, then in this case, and most likely we will not be able to implement or add it. So then we can do the second approach, that we can schedule some online meetings and discuss how to add features in this case. And then we can show you that, and if you want to add this, for example, if you want to enable using adding a new design variables to this province, then we can have meetings, and then we can show you, oh, this is what you need to do, and then we can have multiple meetings and to review your developments. And this is the second scenarios. And eventually, we want these new features added to the main repository. This is the one main mechanism we want to propose in the futures, and to make sure that if you want a new feature, it can be added to the code. And I think the main thing is that we can have online meetings to discuss how to add these new features. Of course, and other approaches, including add more documentations, tutorials, and we also will encourage merging your developments into the main repository. Okay. I guess that's my proposed approach. And now we can have a discussion about any other ideas, or you don't have to ask questions about this feature request. If you have any other questions about how can we help you either use or develop DAFoams, please feel free to ask. Yeah, we have about 30 minutes to discuss this before the break.
Yeah, I think so. What we do is we have meetings with Ping, and I think that's pretty good, and it's worked quite well, because it took some time to reach a certain level of understanding of how the code works. But I suppose meeting regularly, like spaced by about 2 to 3 weeks in between, so that we can get some ideas on how to do things, and we can get our hands dirty and go into the code and start making some changes. So I think that would be a little beneficial. And this is not to say that the GitHub discussions are not useful. I think that should continue, because the response there, I mean, like, kudos to you, Ping. The response there is like really quick. So I don't think that that we should stop that. But I think the scenario 2, which says schedule online meetings to discuss how to add features, I suppose that is also something we can do. Or maybe I was thinking something along the lines of, after having developed a feature or had a discussion, if we could put it on the GitHub discussion portal, I'm sure instead of everyone having to have personal meetings only with you, someone who's worked on some aspects, who are proficient with it, for example, I don't know, handling the geometry parts of it, who've done an implementation, who know how things work a little bit. So we could have interactions among each other and have online meetings with each other instead of having it with you every single time, because I'm sure it can be quite overwhelming with so many of us sort of reaching out to you and you having to have these online meetings with every single person, and kind of takes away a lot of time. So yeah, that's what I think.
Yeah, thanks. I totally agree that the whole purpose of doing this is I want to make this sure the development itself in DAFoam is kind of what we call self-sustainable, meaning that and yeah, in terms of the meetings, maybe I can elaborate on a little bit. These meetings are open to everybody, so I will post the link and the time. Say we have a new feature request, for example, adding the capability to handle supersonic flow problems. This is obviously something, and we can't directly develop because it needs a lot of time, right? And we don't have a project for that. But if you're interested in developing this new feature, we can point to maybe have some meetings, and I'm thinking of what's the best way to reach out to everybody who might be interested in this. Is one way is to post this meeting information maybe in the discussion as well, or maybe I know that somebody has I have your email for those who sign up for the workshop. Maybe send an email, say, hey, somebody requested for this supersonic flow optimization capability, and we can have a meeting at this time, and everybody is welcome to join, and then we can talk about some potential approaches we can do that. So as Yufei just mentioned, that, for example, DAFoam is obviously not the best approach if you want to do transonic and supersonic flow, although it can handle some low transonic case. I know that there are other solvers, like they are designed, these are written in open form. They are designed for supersonic flow problems. One thing I know is HISA. The other is I don't remember the names. But they have some very advanced, they are dedicated for super and hypersonic flow problems. But the problem is that the adjoint is not implemented there yet. So this is something definitely needs a significant efforts to develop. But what I'm thinking of is maybe start from some simple cases and then have some online meetings and have an open discussion in terms of, hey, if you want to develop it, or some team wants to develop it, this is what you need to do. First, you need to add it into DAFoam, second, something like that. Anyway, I want to come up with a standard way such that if people have some needs, and they can get started, something like that. But what you said is, I guess, is a good suggestion that we will probably put that on the GitHub discussion as well. Yeah. And one thing I want to highlight that requesting for new feature doesn't mean that if you publish paper, you have to include me. No, it's just we can help you how to develop it, because we are not going to develop it. And this is, but we still encouraged you to, if you develop a new feature, we still encourage you to merge that into the DAFoam repository. In fact, if you create a fork, we can already see your developments, and it's also easier. Wutan and I are already doing this. He created a fork, and I can see your source code, the new features you added, and I can send a message, hey, you need to delete this line, you need to add this line, something like that. Yeah. Other suggestions or other questions? Okay, so I guess if we do not have more questions, we can stick with the plan. And what will happen next is that now it's still a little bit earlier, but it's close. We will have a break. The plan was from 12:30 to 1:30 US Eastern Time, but since we are early, and we will still have the break until 1:30 Eastern Time. So we'll come back at 1:30, and then continued. We have 3 presentations in the afternoon, and then after that, we have some other discussion. Is another discussion section if you have any questions.